Hello? Hello? Check, check, mic check. 1, 2.
dois. Bom dia, bom dia. Ei, 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 ei. Ahá. Ei, ei. Ei, ei. Ora, bom dia. Ora, bom dia, 5, 6. Ei, ei. Bom dia, bom dia. Ei, ei. Ei, ei. 5, 6, 7. Ora, bom dia, 5, 6, 7. Bom dia. Ei, ei. Bom dia. Ora, bom dia, bom dia. Ei, ei, ora, bom dia. Dois.
Wait, wait. We just got this thing here. You know the internet? Is there internet?
No, I'm using the phone.
Okay.
I don't know about any Wi-Fi. I didn't.
You mean Wi-Fi?
Yeah.
Splash
Splash?
2023.
Okay.
Splash underscore 2023 is the password.
Okay.
Okay.
Thank you.
Splash
Underscore
2023.
2023 is a password.
Okay. Okay. Thanks. Yeah, they're supposed to. First time in life, I only get this badge here, but anyways. Okay. Thanks. For student volunteer?
Yep.
Cool. I don't know who the video person that's gonna be here is, but do you know what to do generally?
Sort of.
Okay. Basically, why is the video? Okay. Hello, hello. Hello, hello. Hello. Hello, hello.
Yeah, he said that the sound from the microphone would be very low on the speakers in the room. He said that the sound from the microphone would be very low on the speakers in the room.
But it's not even coming at all. Maybe they turned it off, but I want to make sure that it's being recorded. Hello. Do you know where to find the YouTube link? Streaming?
I do not know.
Okay, this is a very weird laptop. Volunteers, volunteer, volunteer. Wow. Don't know what to do. I have no idea. Have you used Discord ever?
What did you say?
Do you know this app, Discord?
Discord. Yes, yes.
But how do I even post something? I don't understand. Where? I can write my message here, but then what? Why is it not coming?
Go to the end. Okay, I think this you don't have permissions to post here. I think this is very only for.
Mm-hmm.
But there should be a help channel somewhere for the volunteers.
Can you ask on the channel like where to get the link, because we need to monitor the link. Like I mean I need to monitor the link, but I don't know where it is and no idea if it's being recorded or not. Hello. Oh, maybe there is a link. Okay, wait. There is start recording. It's already working. Streaming is working. Hello. Hello. Yeah, I think it's there, but there is no audio. Hello. So why is there no audio? Can you please help me? Can you just go there and speak something onto the mic and let me see if it's working here?
Testing, testing.
Say it again.
Hello, hello.
Yeah, it's working.
Hello, hello. Testing. It's getting picked up.
It's very little, and it's not like very strong. I'm not sure if it's audible. If it will be audible. Or maybe it's. Can you again try it?
Hello, hello.
Okay, fine. Cannot figure out how to turn this off. Hello. 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 Hello, 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 hello. Yeah. Hello. Is the audio coming?
No. Go.
The audio in the streaming is not. I don't know. It's not coming. Hello.
But it's getting in.
Yeah, but it's not here on YouTube.
But it has to be. It's not from here.
Mhm.
Once it's getting in,
Mhm.
it must be a software issue, a configuration.
It's a
we
delay.
can hear it. There's just delay.
Sometimes there's 20 seconds of delay
Okay, cool.
when you stream to
Got it.
YouTube or Vimeo or something.
Okay.
Ora, bom dia, bom dia. Ei, ei, bom dia. Super low. There's no need to have some.
I don't know if they have one-stop registration.
As a video or music. But then you have situation. In that case, what?
Yeah, they wouldn't be able to print one now.
Just a matter of raising the volume.
Okay, well, thank you for coming. I didn't know you came just for the workshop. In my case too, I came from
Stereo.
Japan
Oh, it's
yesterday,
off.
like at 1:30 in the morning.
Oh, okay, got it.
And
One, two. Ei, ei, ei. Aha.
tomorrow morning.
All good?
It's been too much traveling. Like been to San Francisco, then Japan,
Now, can we
and
try
now
the thing?
here.
Can you just
So like more than around the world, 25 hours. I just want to go back.
No, it cannot raise.
Hello, hello. Hello, hello.
Yeah, because the venue is too remote,
You
right?
did,
The
yeah.
airport is not so
But I cannot turn it
easy
off.
to get
No,
to.
don't turn
Not
it
so
off.
many
You
flights,
can,
and
but don't do it.
It's easier on the
Yeah, it's
this is
easier on that
also
one.
Okay.
a small place.
And when does it start?
Oh, it looks nice. I was
It's just such a
jogging
So welcome.
Sorry, you have to talk in the mic.
Oh, there's okay. Oh, okay. So okay, well, welcome to this 9th edition of this, now ACM International Workshop on formal techniques for safety critical systems. So the first FTSES, took place in Kyoto in 2012. So and since then we've usually, had quite successful workshop with 25, 33, 42, 46 submissions and so on and so on. So unfortunately we didn't get this year so many submissions, only 7 unfortunately. But however, we made sure that the papers were very good because we did not want to compromise on the quality of the event because we are not wasting other people's time or our own time for that matter. So to produce. So anyway, so it's all should be a good program, which we'll come back to soon. So in each workshop, all of them so far have had science of computer programming special issue, and we hope to have that as well this year. So we are currently dealing with Elsevier on that with with these leaders. So. So as I mentioned, right, so we think, at least, for me, right, so with my background and so on, the program looks very nice. So we have had some standard topics or, that we've had before as well, like railway systems and medical devices, which are, of course, key, key application domains, key safety critical systems, obviously, right? So where 4 methods, should have, or has a potential of huge impacts. So I'm very looking forward to those things. And then there's also talks. Santiago is now is chairing a different workshop or conference, but he will give a talk on very efficient techniques, actually improving my own stuff from last year, but for model checking real-time systems using both SMT solving and narrowing and so on. And finally, we also have an excellent talk on program language and safe connections and on fault trees. So it should be short but interesting things. So I thank you all for coming and for submitting papers. So now I'd like to introduce our invited speaker, Professor Kyo-Min Bae from POSTECH in Korea. So he's sitting here, and cyber physical systems, as you've sort of already mentioned, have always been sort of a key topic for FTSES, right? So, this is core, modern safety critical systems. And these cyber physical systems, they are, of course, networks, right, of advanced control programs and continuous physical environments, which means that they're very hard to analyze because, how many tools or methods can deal with very complex discrete program controllers as well as continuous dynamics, right? So anyways, it's my pleasure to introduce Kyo-Min, who is, I think, already now, fair to say, already now one of the world's leading researchers on model checking hybrid systems. I think that's not an exaggeration. CPSs with, as I said, continuous components and complex control programs. So so what we'll talk about today is signal temporal logic, which, to my understanding, which maybe there's subtle differences, but is essentially metric temporal logic, so temporal logic with time, but where the atomic propositions are propositions on continuous values or signals, I guess they're called, right? So, but the key thing is that this is now becoming very, very popular natural temporal logic, natural variation of metric temporal logic for specifying properties of safety critical cyber physical systems, right? Because they have continuous behaviors. So, however, model checking as signal temporal logic has been basically impossible, very hard, right? And impossible. I think there was no sound and complete model checker until in the Popple 2019 paper, Kyo-Min presented or developed the first sound and complete model checker for signal temporal logic, if my understanding is correct, right? So. And that has since been significantly improved. So in the papers at CAV, in papers at ASE. So and my understanding is now that this is the best model checking for STL, best model check for STL, this STL-MC that you have, right? It's not my field, from this CAV paper also. So. Furthermore, to say something more is that not only this STL model checking thing, but there's also this project that Kyo-Min and I have had. Mostly, he's done the excellent part of the work where we all give semantics to a sort of hyper extension of this embedded system standard language AADL. And then so Q-Ming also did, or mostly him, then did a mole checker for that as well with hybrid systems, which turns out actually to, in many cases, outcompete these hybrid automata reachability analysis tools like SpaceX and FlowStar and so on, right? So clearly the Q-Ming knows something about how to mole check hybrid systems. So, to the bio, I think Q-Ming got his PhD at University of Illinois, Urbana-Champaign, under Jose Messager. So, and then he was then, so impressive, so that, Ed Clark wanted him as a postdoc at Carnegie Mellon. So, the Turing Award winner, father of mole checking, right? So, and then after, Q-Ming did excellent there, he then got a position. He was employed at the computer science labs, at Esra International, one of the founding nodes of, computing, especially also, DARPANET and so on, right? So, but then eventually, family call and so or whatnot. So, he went back to Korea instead and got a position at, PostTech, which is sort of building up to be one of the best universities in Korea. So, welcome. So that's so thank you so much, for accepting our invitation to give me a right to talk here. And well, the floor is yours. Thanks.
Yeah, thanks so much for kind and quite detailed introduction. So actually, you summarize my work and presentation today. Thanks so much. Okay, so just wonder whether still the screen is okay here or.
You can have slides.
Yeah. So. Oh, should I just? Okay, probably mirroring, right? The famous mirroring should be done. Okay. Should be.
Can you mirror the display?
Oh, wait, is it? Okay, so is it this one or this one? Because some. Yeah. Because after
Maybe you're right.
orange. Oh.
It's just.
Okay. This one? Oh no, sorry.
I think no. This is what you were supposed to do. This is not even the same mouse. Did you connect to it?
Oh yeah, so it's connected.
So we still have 5 minutes until the presentation, so don't panic.
All right.
Okay, I'll just.
Okay, so probably have to test earlier.
Because this is 9:07, right? So that seems sort of static, right? So
Okay, so
is it 9:07 a.m. now? It's not, right?
No.
okay. So,
You didn't get
Yeah, this seems to be a different thing because there's a mouse here. Why is there a mouse here? There's a different mouse. There can be only one mouse cursor in a computer. Why is there an extra mouse cursor here?
looks like this is not my screen. Explain the first slide. And so the title is a bounded STM checking for hybrid system. And as Peter already introduced, it's a model checker for signal topology properties of hybrid systems. And then this is a joint work with my two students, Jia Li and Gunya Yu. Right, that's the first slide actually. And supposed to go to the second slide.
Well, I mean, it's one session, right? So it's, you know, I mean, the opening and then talk, you know, is usually one thing. So.
Or do you have USB drive? Then I can copy my slide and probably put there. The computer might be also possible.
Sorry, what did you say?
If I have a US drive and then if I put my PDF slide there.
I don't know which computer this is. That's the
Okay.
I see.
All right.
This is not this computer for sure. This is not a Mac. This is
All right.
a Linux or something.
That's true. The
Is there any other
top
computer?
bar
connected?
is from a Mac.
Is it my computer? How can it be even connected?
Maybe you didn't turn on mirroring. And it is your
Oh, actually I disconnected.
Oh, it's disconnected.
Yeah, disconnected and show something. And it's confusing because, you know, I also use default.
So you have the same background.
Yeah, same background. So that's kind of confusing.
Connect the cable again.
I think it's somehow stuck at some initial configuration and it's not going back.
Yeah, it's actually a good idea to have some different background.
We need room for meeting source.
Yeah, that's important.
I also see, but I also kind of, no, oh yeah, because I never see the background because I have so many windows. Yes, so there's, does this take photos, Kimi, or not? Yeah, this takes photos, right? Yeah, now it, okay.
Sorry?
Can you tell me start?
Did you say that?
No.
You might want to smile over it.
He says it's fine.
I don't want to change it. Release change configuration. Change anything. I can remove this. There too many projection.
Oh, it's finally.
Thank you.
Good. Right. So can I? Because it's no time.
Yes.
It's good too. So now it's okay, or?
Yes, yes.
All right, good. Thank you so much, and then thank you for your patience for usual technical problem. Yeah, it sometimes happens. Okay, so let me go back, and then thank you again for kind introduction, and then I'm now going to talk about present my work, boundary STM checking for hybrid systems, and probably first of all I have to thank to the organizer, Peter and Cyril, to give me opportunity to present my work here, and then it's quite an honor. All right, because I have no time, so yeah. Okay, so probably many of you already know, but it's quite related. I just briefly summarize background on temporal logic. Yeah, in usually temporal logic specify properties for computation of discrete systems, right? And then linear temporal logic. Actually, it's quite close. Huge relationship is a signal temporal logic. It's properties of a sequence of states. And then this is the one example. Whenever x is less than 1, the value of y will eventually become 0. Can be explained in LTL using famous square and diamond operator. Right? And then I use this formula for STL as well. And of course, more checking ask whether all possible behavior of the system satisfy this temporal logic formula. This is a typical discrete system situation, but for hybrid system, which combine both discrete and continuous behavior. So the discrete part could be just the usual program or transit system, and continuous part would be represented some continuous function or ordinary differential equations and so on. And then, of course, already Peter introduced cyber-physical system, one of the example of hybrid systems. Yeah, and then here, if we consider precisely the behavior, then actually you have to consider these continuous signals because there is, of course, discrete states, but many important properties are given by changes of these continuous variables over time, like position or velocity, something like that. Therefore, you have to consider that. And then signal temporal logic is a property to specify properties of those continuous real-valued signals. And as a simple example, suppose you have some two continuous variables, x0 and x1, and then suppose they change over time like that. And they are not linear because there's a slight curve over there because it's generated by our tool, but yeah, looks like too straight, but it's not actually. And then probably you can consider some time-related property like that from 2 to 4 seconds, whenever the value of x0 minus x1 is greater than 4, then after 3 seconds, before 10 seconds from that point, the value will be less than minus 3, something like that. Yeah, although in natural language it's slightly confusing, but if we written in temporal logic, which is quite similar to the one for LTL I just mentioned, but you may notice that there is some time bound annotates the temporal operator. So for example, for this square operator, this means that from 2 to 4 time unit, the formula inside this parenthesis must hold. And then this diamond say that from time 3 to 10, at some point, this proportion hold. Therefore, by combination, at any point from 2 to 4 time points, right, this will hold, and this means that during this point, whenever this hold, then from that point, from 3 to 10 time unit, for some position, some moments, this condition hold, right? So slightly a bit complex, but it's quite similar to LTL in some sense because the only difference is that this interval gives some restriction about the moment of events. Yeah, and then this actually extends the syntax of LTL with local timing constraints, like interval, and then, as mentioned by Peter, is syntactically identical to metric temporal logic for real-time systems, but semantically it's different because it involves some continuous signals and so on. Okay, so and then this STL proposed like a 2005 around there, and then after that it's widely used for monitoring and falsification. That means given simulation or testing, which will generate some concrete signals, the monitoring check whether that generated signal satisfy this STL requirements or not. And falsification is to generate or synthesize counterexample by somehow various simulation and then optimization techniques. And then they turns out to be very effective for analyze concrete samples of signals to find the counterexamples. Yeah, and then there's so many different techniques and tools for that purpose. But as usual, although they are very useful to find some errors, but they cannot guarantee correctness. And also, it's slightly difficult to find some subtle errors using those techniques. Yeah, just some typical situation. And then there are also some verification technique or model checking technique of hybrid system exist. It's also since almost mid-90, more than 30 years ago. There, the hybrid system specified as some mathematical notation, and from there, it's possible to symbolically analyze all possible behaviors. But those techniques mainly focus on invariant and reachability properties, or their slight variation. Yeah, so there's so many techniques and tools for analyzing invariant and reachability property to guarantee correctness for hybrid systems. And then by slightly modifying that or generalizing that, it's also possible to check simple, very specific form of state property, like that, given initial condition, whether some invariant hold like that. But ST model checking for general ST property is previously not much studied. Probably there are several reasons. One is that even for invariant and reachability properties, the speed performance is quite slow, yeah, for obvious reason, because have to consider infinitely many signals and so on. So people focus on improving the performance of this reachability analysis techniques for many years. Okay, and probably that's a main reason. And also for general state property, typical technique used for metric temporal logic is not that effective. Therefore, yeah, it's good to, of course, develop some technique to verify general state properties of hybrid system, and then that's the motivation of our work.
Any other questions?
Sure.
In your example, with just two values, we could do predicates. In your example, you could do a predicate abstraction if it's just two signals and inequalities. And then, to me, it feels it would be fairly efficient, but maybe in more complex cases, this wouldn't work anymore. What is the reason?
Predicate abstraction technique? Or?
Yes, for example, there are certain intervals where the difference is greater than 4. Mm-hmm. So you could have a Boolean and track just that and the interval, and then you could, in this case, maybe reduce it to regular.
So it's slightly more complicated, because here actually the meaning is that, for example, for any moment like that, say time 2.1, if this hold, then from time 3.1 to 10.1 this hold, and then say 2.2, 3.2 to 10.2 this hold, and so on. So therefore, it's not easy or immediate to just split the interval.
Okay, because of the nesting. Okay,
yeah,
thanks.
Because of nesting. Okay, so actually it's a very good question, because I mentioned that model checking for invariant and reachability and some variation exist. And then actually, when the interval can be specifically separated, then that's actually easier, and then there's several techniques for encoding that as hybrid automaton exist actually. But actually, that might be possible, for a general STL property as well, but it's not been developed. And then a part of this technique I mentioned today can be also applied to generate some hybrid automata as well. Of course, it's out of the scope of this talk. Actually, it's my future work. But yeah, so because of this arbitrary nesting of the STL formula, it's not that clear how to do that systemically. Yeah, although it's possible, but unless not developed previously. Okay, so any other question? All right. And this also applies to metric temporal logic as well. So, because you know.
Sorry, a quick question. Did I get it right? Is the intervals, are they all with respect to the global time point 0, or are the intervals to be interpreted in a relative manner?
It's actually a relative manner.
Okay.
So top one is with respect to 0 typically,
Mhm.
and then the nested one with respect to the just above one, and so on.
Very good. Thank you.
All right. Okay. Yeah, and then of course for developing this STM technique, there are some typical challenges. First of all, STM checking is generally undecidable. That's kind of obvious because you know even invariant property is generally undecidable for some general hybrid systems. Of course, for very strict hybrid system, that can be decided like a timed automata case. Timed automata can be one of the hybrid system as well. You're right, but it's generally undecidable. And second one is that boundary model checking of STL is also difficult because boundary signal can be any arbitrary complex. For example, given any fixed duration of interval, we can give arbitrary complex behavior. For example, by increase this number 10 to 100 or 1,000, we can have very complex behavior, arbitrary complex behavior. Okay.
So just to be sure, because maybe. So signal, you said infinite number of signals, but isn't that? I mean, isn't this whole thing one signal? I mean, I mean, so a trace of X is one signal, right?
Oh, this is as a to illustrate purpose.
Yeah,
It's
okay.
typically given as ordinary differential equation with different initial value.
Yeah.
So basically, in practice, some parameter of initial value will be different. Therefore, given arbitrary initial value for a specific duration of a signal.
Okay, so it's, but in general, I mean, signals are sort of deterministic and so on, right? So
if
once you start,
once you started. But you know, for specific discrete state, the number of initial value for that state would be arbitrary. So, and also it's possible to allow arbitrary control input from outside as well. So in that case, the dynamics itself could be infinitary as well. Yeah, and then in this talk, I'm not talk much detail, but robustness of STM checking is even more challenging because you know, for discontinuous signal, if there's small error in sensors and actuator, then the truth can be just changed, right? So by giving very slight difference, verified property could be violated and so on. That's not desirable. Therefore, some kind of robustness is important, and then how to deal with that for verification is also important. Okay, so basically, our approach to address those general changes is to perform bounded model checking of STL properties for hybrid system using SMT solving techniques.
So, if you can go back to previous slide. So, you said this arbitrary complexity of the signal, right? But I thought you made it discrete. But once you make the thing discrete, that signal can only take some value for this result is still hold about understandability?
So actually, it's related to previous question, right? So
Oh yeah, okay.
if the given state,
Mhm.
because there could be many different discrete state, if the initial value for that state is fixed, then usually the signal is deterministic, but the initial value could be in some interval as well. So basically, infinitely many initial value for a certain discrete state. Yeah.
So if
For
you
example,
also, like
for example, for
limit-
this example, initial value of x, y, and theta could be some interval for the first mode, and then when changed to different mode, there could be another interval, and so on. Therefore, there could be arbitrary complex behavior. That's typical. And then another thing is that actually continuous dynamics can have also arbitrary control inputs from outside as well. Although the control input itself is assumed to be piecewise linear, though. Therefore, could
just to
Mhm.
follow up, like, so if we limit the value of the signal to be discrete, like it can only be some value, and
Mm.
it has to be constant for like every small duration, let's say epsilon,
Mhm.
then you have the whole system to be
Yeah, yeah,
completely
so
discrete, and then
exa-
it's everything is like can
Yeah.
be reduced to LTL, I guess, right?
Actually, there's a dedicated technique called STM monitoring. So STM monitoring technique try to efficiently compute given concrete signal, initially fixed and then all the behavior fixed, to efficiently compute the truth of given signal with respect to STM formula. Yeah, there's an extensive study about STM monitoring,
Thank you.
and it could be very useful for testing, but because yeah, right. But because you have to, it just rely on some sampling of finite number of values, therefore cannot guarantee correctness. All right. Okay. And then the goal is reputation complete for boundary signal. So there exists some previous technique that insists STM monitoring, STM monitor checking, but the problem is that it's mostly about sampling as well. So typically, does not say correctness is guaranteed up to certain bound. So therefore, I wanna have some good property for bounded LTM monitor checking. So for bounded LTM monitor checking, you can say that up to some number of discrete transition, the correctness can be guaranteed. Then question is, how can you do that? And then also robustness. Turns out to be actually quite simple though, but it's also important to define, provide some robustness up to some threshold or error bound. And finally, you wanna develop tool, STLMC, actually developed, of course, that can deal with general STL formulas. All right, so let me briefly overview some detail again. Okay, so basically I mentioned that you want to develop some bounded monitor checking technique for STL, just like there exists bounded monitor checking technique for LTL. Of course, for LTL case, typically you can do that using SAT solving, but STL, you want to do that using SMT solving, together with some specialized solver to support nonlinear dynamics or even ordinary differential equations. So for LTL case, so we can reduce the the monitor checking problem to satisfiability of proportional logic. And then the idea is many of you already know as follows. First, the computation of a system up to certain bound number of transition can be encoded as a SAT formula. And at the same time, the existence of LTL counterexample up to certain bound can be expressed as a proportional logic formula. So, and then that can be done by some famous equivalence. For example, for always phi formula, basically we can say the first state is satisfied and second state is satisfied and so on. And then for eventually phi formula, it's either satisfied in the first state or satisfied in second state or and so on, right? And then for more complex formula like until formula, similar rule can be defined. Therefore, by using the kind of equivalence or translation, you can easily encode LTI formula as SAT formula, which is proposed in late 90 by several researchers. Okay, then for boundary model checking of STL, then how can you do that? So as you mentioned, we want to reduce the satisfiability to SMT problem or first order logic problem. And then, okay, similarly, we need two things. First, you have to encode the behavior of a hybrid system up to time bound. And that's already done by another work, because I mentioned that model checking technique for invariant and reachability are studied extensively for hybrid system. And then this is exactly the related to the technique for model checking invariant and reachability problem. So this is good. But problem is that for second one, encode the existence of STL counterexample up to some bound. And then some immediate difficulty is that there's uncounted number of states over continuous time with nesting. There's already asked several times by in the question, and then this could be arbitrary nesting of different formulas and so on. And then the computation is not really bounded. And for a real-time system, typically we assume non-zero behavior, right? So that the change of state should be only a finite number of times and so on. But by definition here, signal temporal logic, the change of states could be infinitary. So therefore, we cannot assume non-zeroness of real-time system and so on. And then actually here, the solution is quite simple, because we can just consider similar properties non-zeroness of real-time system. But slightly different thing is that in the real-time system, non-zeroness means that the change of state itself is finitary. But here, we require that the change of the truth value of a subformula change finite many times within a fixed bound. So it's a kind of non-zeroness condition with respect to subformulas. So you say when some truth value of formula change, we call as a variable point. So you just assume that. So therefore, you want to model check STL formula with respect to finite number of variable points. Therefore, the bound parameter would be these variable points. Okay, so it's a simple idea. And then we can freely limit model checking computation involving continuous behavior, like the previous example of this arbitrary complex signal. The number of, if we limit the computation up to number of variable points, then it can effectively bound it. All right, so just to give us some shortcut notation or terminology, I say some STL formula is stable in interval if the truth of the formula does not change within the interval. All right. So basically here, if those time points are variable points, then truth of the signal with respect to formula in each interval in the middle, the STL formula is stable. All right. Okay. So the first idea is just to perform that kind of technique. And this is just a brief overview of how to encode hybrid system itself in SMT. I mentioned these are already studied for a long time. So basically, in a hybrid system, we assume that the state is given by some discrete state, say Q, and some real valued vector. And then the encoding defines some initial condition where the initial state must satisfy. And of course, this is just condition, so therefore there might be infinite number of concrete states that satisfy this initial condition. And then the continuous change could be defined as symbolically some SMT formula written this flow that means given some initial value for duration t0, the resulting state will be this free zero t. Okay, so this can involve some arbitrary continuous function or ordinary differentiation, solutions of ordinary differentiation and so on. And then you can typical discrete jump from some state to another state. All right, so basically by conjunction of this initial flow jump, we already describe or encode the behavior of hybrid system in one step. And then by repeatedly doing that, we can easily encode the reachability problem or invariant problem of hybrid system in SMT. Okay, so that's somehow easy and well understood. So actually we wanna use that for system representation or system encoding. And of course the only problem now is how to encode the property part. Okay, so basically in order to encode the property, we just assume given STL formula and some variable point bound. And then as I mentioned that basically we just want that truth value of each sub-formula is stable, all right? So basically there we provide two things for our encoding. First, we have some SMT variables to denote the times, right? For example, if there's a k variable points bound, then we can provide a k SMT variable to denote each variable point in the position, right? And then those time points will provide some interval for 0 and open interval 0 to tau 1, and tau 1 to tau 2, and so on. So this graph show some potential instantiation. Okay, and then for now, each subformula, you wanna provide some truth value. Okay, so for example, for this formula, there's 3 other subformulas. Then we just assign a truth value as a Boolean variable. Okay, so in our SMT encoding, so basically we have a SMT variable for each variable point, and then truth value for every subformula. Okay, so those are all the variables needed actually for encoding behavior of STL property, right?
Hi, I think I missed it, but is this partition, doesn't it depend on the initial condition or something? Like, is it unique for a given?
Oh, actually I say there is SMT variables. So those are variables for SMT encoding. So basically,
you're not generating the partition. It's some symbolic like partition. For
yeah, symbolic partition, exactly.
Thanks.
Yeah, because just assigning those variables are not enough, of course. And so we need extra condition. That's actually SMT formula, right? To exactly define symmetric relationship between those SMT variables. Okay. Yep.
So maybe I missed something, but this whole encoding, of course, given a variable point bound k.
Yeah, exactly.
Where does that k come from?
From user.
Okay, from user.
Yeah.
Okay, so it
Yeah.
comes from user. Okay, so that's
Yeah, good question. Thank you.
that's the
Thank you for
hack here.
clarification. So basically, just like typical LTL model checking, where the user must provide bound. LTL boundary model checking, the user provide the bound, right? So actually here, the user provide also this variable point bound. Yeah, because even having the bound from the user, we can increment the bound from 10, 20, and so on. So that's what's possible. So there are two ways. Either the tool automatically decides by heuristic some initial bound and then increments the bounds, or user can just give a hard bound. Both are possible. All right, it's just a typical bounded model checking scenario. And then there, for STL encoding, we need several symbolic variables or SMT variables to describe time points and then truth of each subformula. So therefore, if we can define some SMT formula or first logic formula to exactly capture the relationship so that satisfiability of this formula, that means that the question of finding some assignment to those variables is equivalent to STM matching problem, then we are done, right? So then the question is, how can we find some encoding to make the satisfying assignment for this variable is exactly equivalent to bounded checking, bounded STM checking problem. Okay. Yeah, but of course there are some challenges you have to consider. But by the way, some end question. So I think that there's some high-level idea I try to make. So yeah, slightly detailed, but for the algorithm level or encoding level, this is the highest level of explanation I can have. But if there's unclear things, then feel free to ask me. Is it good? Right? Thank you. So one thing is that for LTL, actually it's easy to identify some subformula that only depends on specific part of system. Right? In the LTL, there's a next operator. So next operator say nth. If there's a 2 next operator, then it denotes second state or third state or 3 next operator and so on, right? So basically in the LTL, it's kind of trivial that each subformula related to specific state. But in STL, it's not actually, because of this time interval. It's not clear how to have some kind of semantic fragment of each subformula for each interval. So, for example, consider this formula. Then for the second interval, which part of the formula related to that? Yeah. So, right. It's not clear because of this overlapping of interval. I can give you some example later. And the second one is that basically the size of encoding depends on number of these time variables, right? And then, of course, having the minimum number of those position time points, say exact number of variable points, that might be ideal, but it's not actually easy. Therefore, typically we need more time variable. It's still stable, but it's not optimal. Then question is how can you reduce the number, right? Because the redundant time points can make the analysis very slow. Yeah, as you can expect. So as you can expect, STM knowledge checking in our approach is by default as slow as existing invariant knowledge checking, because we use invariant knowledge checking subroutine. And I mentioned that because invariant knowledge checking is already slow, therefore people focus on that, right? Therefore, it's a good idea to at least avoid some redundant computation. Okay, so each of these idea or difficulty can be addressed by the technique I mentioned now. So for the first question, we consider some syntax separation. It's actually typical in LTL. So LTL naturally supports syntactic separation, extensively studied in 70s by several famous Kemp theorem and so on. So it's basically we want to obtain some equivalent formula where the satisfaction of each subformula all depends on specific time interval. For LTL, depends on specific state, but here a specific time interval. Right. So for LTL, I state, but STL for specific time interval. But that's by default non-trivial. For example, consider this example. Actually, I already mentioned this several times thanks to several questions, but now I graphically show the example. So this means that for any time points between 0 and 2, say u, the interval from u plus 1 to u plus 3, the q must hold at some point, right? So basically, for any u, there's a u plus 1 to u plus 3. That's actually related to a serious question, right? Because of nesting. So therefore, no formula of this form. So even if we manipulate those formula using standard STL syntax, but no formula of this form can exactly capture some interval. So probably you need slightly more, right? So for the LTL, because of its simplicity, we can exactly use the same syntax for syntax separation. But for STL, separation is possible, but it's not disjoint. Okay, so it's a more concrete example. Suppose that this formula again. Now suppose that we want to separate the formula, top formula only at time 2. Okay, then actually I mentioned that separation can be done. So actually in this case can be done very easily, right? So from 1.1 to 2, this hold, because you want to separate at 2. And then exactly 2, this hold, and from 2 to 5, this hold, right? So looks okay, looks good. The problem is that the first part actually depends on interval 1 to 2 because this part, x greater than 0, corresponds to this interval. And then this interval corresponds to sum of this one and this, therefore correspond to 2 to 5. Okay. And similarly for the second one, this truth depends on 2 because x greater than 0 depends on 2. And then 3 to 5 because, you know, this guy depends on 3 to 5, and so on. And therefore, each part has some overlapping. So basically, this separation, this natural separation, cannot provide this total independence. Yeah, might be possible to encode to provide SMT encoding without that disjointedness. That might be possible, but actually our idea is to have some same situation as LTL. And therefore, if we allow total differentiation or separation, then SMT encoding might be very easy. Therefore, the question is how can you do that? So that actually the idea is that we don't need to stick with STL syntax because this STL separation can be only done inside encoding process. Therefore, of course, for the user, want to have the exact representation, but for the algorithm, we don't need that. Therefore, actually, we just consider slight variation, STL with global time. Okay, so it's related to another question, right? Because yeah, you just want to add global time as well. So then truth of self formula become vacuous outside of the global formula. Therefore, you can naturally distinguish or make independence all the sub-formula to specific interval. That's very easy now, right? For example, by adding this global interval, we say we put global interval as a superscript, then means that this operator say the previous meaning of the usual STL operator plus only consider this global interval. Okay. So therefore, it's trivially the truth only depends on the interval. And then the syntax separation can be much easier because we only need to put some separate interval at the global level, and then we can just leave the local interval the same. Okay. All right. So looks like very simple, but actually this work now involves several other definitions of semantics and so on, so slightly complex. But I skip the detail, but as I mentioned that we are able to define the semantics of that and then some separation rules. Okay.
So these global time intervals, do they split up into more and more intervals with each level of nesting in the formula? Or might they, in some cases, split up?
Okay, probably. Actually, there's an example in the next slide, but for each level, okay, we only need the same thing. And then by using famous formula sharing technique, the size of the formula separation result can be polynomial.
Thanks.
Without sharing exponential, but sharing. It's just like the LTL case, because for LTL case, each subformula separate to specific number. So it's the text size increase exponentially, but internal representation you're sharing is polynomial, right?
So I'm more confused about the meaning of this global interval because of what it seems like that it says that if P is true from 0 to 2, then eventually Q has to be true between 1 and 3. and then you put this constraint of 0 to 2 on the sub-formula. Now,
Okay. Yeah, so it's actually in the natural language, it's slightly unclear. And then, of course, it's clear if I show concrete definition, but it's complex. But it's idea is simple. So basically, you can just assume that existing semantics, just same as existing meaning, except just make vacuous outside of given global interval.
so I can just take intersection of this and say it's basically 1 to 2 then for Q.
Yes, basically, you can consider, okay, if it has a semantics of stereo signals, okay, then without global interval, we can consider some stereo signals satisfying this formula. All right, and then that involves some interval from 0 to 5, for example, right? From 0 to 5. So signal of length 5 will be related. Okay, we just ignore 3 to 5 there. So only consider 0 to 2. So just kind of the given stereo signal is some discarding all other part of that except global interval.
But this is not then directly equivalent to the original formula.
Oh yeah, it's equivalent to original. Ah, okay, this one. Okay, not equivalent, of course.
Yeah, okay.
Yeah.
Okay, so you do it for multiple global intervals. Okay.
Okay, so as I show some example, probably this example might be should appear earlier. So consider this formula. Okay, then you can easily separate you can just imagine at the top level you can separate at time 2 less than 2 equal to greater than 2, and now equivalent, right? Now equivalent, and then the second level you have to also separate less than 2 equal to greater than 2. Okay, looks like exponential growth, but you know this formula can be shared. Therefore, as usual for typical LTL separation, that's show that exactly the same phenomenon. The size is a polynomial with subformula sharing. Okay, because the size is 1, 2, 3, 4, 5, 6, 7, 8, 9. That's all, right? Because all subformula shared. All right. Okay, so now you can understand what will be separation. That's with the global interval is very simple, right? And then there's some result now. The detail will not be shown in this talk. Okay, given separated STL-GT formula, is very now quite straightforward to generate eccentric formula where the satisfier P is preserved. So it's basically given symbolic variables. We can obtain some syntactic separation. We are separated at each time point. For example, for 2, just like that, right? But for some symbolic variable tau 1, you can have a similar separation, right? And then you can obtain a first order logic formula that capture the constraint over eccentric variable over this time variable, and then the variable assigned to each subformula. Okay. And then some theorem is that if this formula is satisfiable, if and only if the phi is satisfiable by signal with m most, not exactly, sorry, but m most k variable points. But there's some assumption. Each subformula of phi is stable in each interval of the corresponding partition, so that each subformula does not, truth of each subformula should not change, right? And of course, in this purple work, we also provide some basic result for encoding this part using existing technique that I'll explain right now. But before going to that, let me know if you have any question. By the way, how many minutes?
You have like 16 minutes left.
1 hour?
16 minutes left.
Oh, 16. Oh, okay. Less than 20 minutes?
Yeah.
Oh, okay. I will repeat. Sorry.
Because it's 1 hour, right? So
I see.
yeah.
Okay, already. All right.
Very simple question, but just to make sure that I got it right, is the ability, the use of variable points instead of time, it makes you able to capture infinitely long trajectories, right?
Yes or no?
If infinitely many variable points are stable, right?
So it's actually yes or no. The yes
Or at
means
least one,
that
I mean, yeah.
if the time bound is just infinite, it's still possible to have only finite number of variable points. And
Yeah.
for certain case, like that, just a typical SMT solver case, we can deal with that.
So if you have one variable point which remains stable for the formula, then you capture an infinite time trajectory, right?
Yeah, for certain case,
yeah, yeah.
not all, because it depends on underlying solver.
Sure. Yeah.
Yeah,
Okay.
but for many continuous solver, especially for numerical solver, the bound must be given. Therefore, for some case like encoded using polynomial SMT solver, like YICE2 or Z3, for other case, in practice, the bound should be given. Yeah.
Just a very quick question. Why did you choose 2 in that when you were doing the global interval? Why? How did you come up to know that 2 has to be the separating point?
Here, the separating point is just symbolic variable. In the example? It's just arbitrary. Yeah, just arbitrary. Yeah. Okay, and the problem is slightly fast, but the idea here is simple. So now actually we wanna accomplish this condition. So basically, given time points, we have some partition of intervals, right? It's alternation of the point and open interval. We say some formula is fully stable if each subformula of this formula is stable in each interval in the partition. Okay. Then, of course, the problem is that we want to have that only proposition is stable in a partition, because that can be encoded using typical reachability invariant solver, invariant heuristic technique. So from this condition, we want to obtain some refinement of partition. For example, refinement is a more the finer partition, typically having more endpoints, right? Here, Q is refinement of P. So we want to build a refinement of original partition P, where now this phi is fully stable. So not only stable for this proposition, we want to stable for every subformula. And then the question is, of course, is does this exist? The question is yes, it actually exists for a long time, because even the early work of metric temporal logic by Arlo and Hetzinger, it's well known that it's possible to develop a fully stable refinement, because it's somehow foundational assumption of timed automata based model checking over metric temporal logic. So the idea is very simple. So given some formula, for example, with endpoint to A and B, and if the subformula phi, immediate subformula phi is stable in this partition for these time points, then for considering additional points like that, original P plus this T minus the left-hand point, union T minus right-hand point. So it's provide more finer partition. By considering these time points, then this is stable. So this is already well-known this work. And actually in the Popper work, we use this result to give reputation complete model checking algorithm. But of course here is some problem, because it does not consider any actual truth value, because given time point and the interval, we have to have a fixed number of time point. Therefore, can generate unnecessary fine partition with unnecessary many time points. Okay, then how can we reduce that? So actually, here is some observation. So okay, this picture is slightly a bit complex, but it's actually simple. So now I explain. So consider this formula, eventually I phi, and suppose that there's a sequence of interval, right? So point, open interval, point, open interval. And suppose that phi is true at this interval J6 to J8, okay? Then by some analysis, proved in our paper, that this formula is true, stably true in this interval. Okay, so basically, given the truth value of stable interval of a subformula, we can obtain which part must be stable in the each temporality formula. It can be also defined for more complex formula like until or release and so on. So actually then now we can observe that instead of all the point, we can only consider rising and falling edges. Therefore, so rising edge means that whether is become first true, and falling edge means true to false, first true and true to false. And then by doing that, of course, we can ignore many redundant position. But of course, we have to keep track of actual truth value. But okay. So example is that suppose that this formula has a partition by this time point, and then suppose that the atomic proposition is stable for all these interval. But even though there's a many time points, 1, 2, 3, 4, 5, 6. There's 6 time points, but there's only one rising edge and one falling edge. Therefore, you only need to consider 2. Therefore, the interval Q, partition Q would be just a P union, these 4 time points where 0 is all the same. Therefore, the size is minimally increased. Okay, so it's a very simple idea. Although it's simple, but actually formalizing involves some difficult step though. But anyway, so we are now able to build a first order formula that define the constraint over SMT variable similarly by this fully stable refinement. And to give us some idea how it looks like, I just show some snapshot. But you should not try to understand this, but just to give us some idea that in the encoding itself, we include that whether it's a going rising edge or falling edge, where rising edge, falling edge can be defined in a usual way like that, through some value and negation at the next step. Okay, well, falling is similarly. So the rising and falling edge itself can be defined symbolically, and then we can encode the condition I mentioned symbolically as well. And therefore, finally, we can give this fully stable refinement condition as a SMT formula. Okay, right? So I just quickly skip that part because Anyway, therefore, we can reduce SMT encoding of satisfiability to just SMT satisfiability. So this formula means that first interval is the top position, right? Therefore, if the original the relationship formula is mentioned in the previous theorem, and then this is a fully stable refinement formula, and then correspond to one top position, satisfiable if and only if this phi is satisfied by signal is at most k variable points. So yeah, now the extra condition shown in previous theorem removed because this new fragment of formula represent that. Okay, by combining them, actually, we can have some SMT encoding of bounded STL model checking problem. So that by having some, as usual, encoding for negated formula, we can say that this negated formula is satisfiable if and only if, okay, encoding of negative formula is satisfiable if and only if the counter example trajectory of phi at most k variable points, and now also mode change, because encoding of the system part require to have k mode change as well. Okay, so it's basically a conjunction of the typical encoding. I just briefly explain here. This is for system interval, system encoding, and the encoding I mentioned for relationship and also free stability. Okay, so by taking conjunction of them all, we can obtain this encoding, and then this can provide encoding for reputation complete encoding for bounded STL model checking problem. Okay, now using that, we develop model checker. And before doing that, we also consider slightly simplified setting of this robustness. So basically, we want to model check, a robust model check up to some robustness threshold. That means for any numerical perturbation up to some threshold, the result should not be changed. That can be actually done very easily because for the first order logic theory, it's possible to numerical strengthening or numerical weakening of some first order logic formula, and then also similarly you can easily define numerical strengthening and numerical weakening of STF formula. That means a signal satisfies some strengthening if all of its numerical perturbation up to this threshold satisfy that. So this is just an extra layer. Okay, and then for algorithm level, you also perform some abstraction, but I just skipped it. It's no time. Anyway, this is now some architecture of monad checker. So we're given hybrid automaton or hybrid system, and then two bounds. One is the discrete bounds and time bounds. And time bound can be infinite though, but for a special case. And then, as I mentioned, using the previous theorem, we can have an encoding of Boolean stem monad checking. Then using this threshold, robustness threshold, we can epsilon strengthening this formula. Then by combining them, okay, now we have a SMT encoding of robust stem monad checking. And then you can use typical SMT solver like G3S2 or D-real for ordinary differential equation. If there's a counterexample, it show the counterexample, and otherwise, it's verified up to specific given bounds and robustness threshold. So, and then this can be reputationally complete by incrementing bounds. Okay, and then we can also implement the various optimization methods previously known for hybrid system, including removing hybrid automata-based removing of image quantification and so on, not quantifier elimination. And then the tool is publicly available at this website. And then this is some demo somehow of the tool. We can provide some hybrid automaton format as usual, but using mode invariant condition, flow condition. Here is given by ordinary differential equation or jump condition. And the tool also recently also support other format like SpaceX format and so on. But this is close to D-rich format, SMT-based monad checker. And then you can declare proposition and then declare STL goal. And then it provides some command line interface using various parameters like discrete bound or time bound or threshold, robustness threshold or solver or some optimization algorithm. And then it can either say no counterexample found or counter is found at certain bound. Okay, and then if counterexample is found, then using satisfying assignment returned by SMT solver, we can draw counterexample. For example, this is for thermostat example. This visualize the drawing where this show trajectory of the proposition, and then this is the trajectory for each sub-formula. Although I didn't mention that each sub-formula itself may have some numerical value because of the no time, and then also it's quite technical. But anyway, this show the counterexample, and then using some experimental evaluation, we successfully perform for typical hybrid automata benchmark for quite complex nested STF formula. For example, for linear dynamics, where the continuous dynamics is a linear function, you can use S2 and then obtain this kind of result. And it's quite efficient somehow. And then for ordinary differential equation, here we use D-real. And the D-real itself is actually quite slow. So basically, it just kind of show that this can be done, but practically often not that useful. But anyway, using D-real solver, we could verify arbitrary complex ordinary differential equation. It's a involve nonlinear ordinary differential equation, and then can verify some complex STL formula and estimate up to some robustness. All right. Okay. Now, because it's time's up, according to the chair, so some summary. Basically, signal temporal logic has been proposed more than 20 years old, and they're widely used for analyzing cyber physical and hybrid system. But previously, it's more focused on deterministic signal. All right, so monitoring or falsification or monad checking is quite limited to invariant and reachability property or their simple variation. And then our goal is to provide bounded monad checking algorithm for general class of STL formula. And then there are to deal with some technical challenges, we consider syntax separation and signal discretization technique. And then using that, we have developed a tool for robust STL monad checking. As far as I understand, is the first tool because there's not many people worked on that. And it is reputation complete, and then able to verify many existing hybrid system benchmark. And then the future work, we are working on now how to do without SMT. It's basically automata-based STL monad checking can be. How can we can perform automata-based STL monad checking without SMT solving for general STL formula, and then so currently we consider bounded signal here. Bounded means finite number of variable points, right? Then how can you do that for unbounded signal? Could be done using some typical existing technique for various certificate and inductions, something like that. But how can do that for STL is also some question. All right, that's all for today. And then thank you for listening. And happy to answer any question.
So this is the beauty of these workshops, right? That we can also ask questions during talk, right? Maybe it's not, but of course also now. But thank you so much for asking in between and taking your time for that. But that's the point of having a small workshop. So it was serious. You still have some question.
Yes. Under what license is your tool available?
Open source license. So I don't remember exact license, but it's one of the open source, I think. Yeah. So what's that? I don't remember. Sorry, but it's open source.
The very standard question. So refutation complete means it guarantees that if there's a counterexample of length k, then it will find it.
Yeah, exactly.
But then the user needs to manage that they choose k properly. Right?
Or tool can continuously increment the bound.
Yeah, exactly.
Yeah, of course, but user cannot wait for arbitrarily long time. So practically there's some bound.
So this is the usual problem with bounded model checking. It's not really a problem because in many cases it's practical. I wonder whether you have some guidance on the diameter of a model, so that the user gets some guidance on what is the minimum k to be chosen, knowing some properties of the model.
Yeah, that's actually a good question. So actually, honestly, I have to say, even for invariant property, for a typical hybrid system, people do not much consider that kind of diameter problem because typically this monad checking of hybrid system, two reasons. People typically consider very simple discrete dynamics involving only 2 or 3 states. So diameter there is visible by head, just by eye. Yeah. And then second one is that if number of jump increase like that more than 100, something like that, even for very simple system, it's not feasible. So therefore, people typically focus on for bounded analysis. Yeah, although there's unbounded analysis that requires some manual intervention and they're very limited dynamics. But anyway, but for some general bounded analysis, the bound tend to be not aiming diameter completeness. Okay, all right, that's one thing. And then, as I mentioned, if the hybrid automata is very simple, then diameter can be just guessed by the longest path without cycle and so on.
Yeah.
But for STL, currently there's no such result, unless in this boundary.
Yeah.
But for the current work we are working on, based on automata based one, it's possible to provide some diameter because it related to generating some automata, and there you can have the same analysis by longest acyclic path. And so,
Thank you very much. That's helpful.
thank you. Yes.
I think we have to. Well, you'll be here for the whole day, so yeah. So just thank you. Well, there's nothing scientific. So thank you so much for doing it. So merci in merci in the French as well, right? So thank you so much for coming here. So
Thank you. Thank you so much.
hope you survived the trip.
Yeah, nice gift. Thank you. Yeah, thanks so much.
What is GOA4, by the way?
It's a grade of automation.
Oh,
Very good
okay.
question. Very good question.
Okay, because I want to read the title and yeah. Oh, that's also like this in the title, but I guess it helps to explain. Okay, before you had it right, and now it's. So just for a moment, it was the full slide, and now it's zoomed in and only half of it.
Okay.
Okay, this is good.
Fine for this.
I mean, it's almost the full height. Yeah, this is good. I think it will.
But if you click X on that top.
On my laptop, it will be the same. No, then you close it.
Oh, you close
No,
it.
that's not good.
Okay.
Why is it
Which
It's fine, it's fine.
why it is like?
No, it's. I think on my laptop it will also be like this in the afternoon.
So
Oh, now we just lost it.
Yeah,
So
I was going
No,
to
it's
try
fine.
to make it
better
larger.
not to. Yeah, better leave it.
Oh, it's good.
Good. No, never change the running system.
Okay, welcome to the first session with the regular papers that we have. So first it will be Mario Gleichner from University of Bremen talking about probabilistic risk assessment of obstacle detection in grade of automation for freight trains.
Yeah, hello, good morning everyone. Thank you for being here and thank you for the opportunity to present some partly ongoing work on risk assessment, risk quantification. Hold on. Yeah. Okay, can you hear me now?
It's not on these speakers, it's for the
Okay. I'm sorry. Right. Does anybody of you know what GOA4 is? I didn't know until just before I completed the risk assessment. So the joke is because the risk assessment is, I'm going to just give a brief overview of what we did on one slide. Is about, so we had the problem of identifying the false negative rate of a fault-tolerant train sensor and reduce it to an acceptable level. False negative means the sensor is supposed to detect something but can't or missed an object. In that case, it was a setting, train's obstacle detection, and the sensors are supposed to detect obstacles on the railway track, and with a certain probability they fail to detect existing obstacles, and this is what we call false negative. And the study was all about figuring out for a particular architecture, which you see here, a little small. I'm sorry for the slide. Should be a little larger. Anyway, it's a 2-channel sensor system with 2 duplicated channels with a sensor component and a perception component, and using the standard voting pattern to decide whether to switch off, whether to emergency brake the train or not, on the basis whether both channels deliver consistent results. This is a fairly standard architecture used in many systems where reliability and fault tolerance plays a role. And what we approached, that risk assessment in the context of highly automated or autonomous train systems, like used perhaps in the future, if we want to believe what people say, on shunting yards where trains are supposed to run around autonomously, and there is a certain upper threshold for the false negative rate that is to be applied according to applicable standards in the railway domain. So what is usually be done is what we also did. We performed a fault tree analysis of the whole sensor module, and in the course of this fault tree analysis, we of course had to estimate component error rates, and in order to figure out to quantify the basic events in the fault tree. For that, we decided to use a stochastic model. In our case, it was a continuous time Markov chain model, and that we used to estimate these error rates, to estimate the overall, the top level events and the intermediate events of the fault tree. And also what we did is then to use parametric model checking to generalize our stochastic model a little. Our contribution is basically a procedure, a guidance for engineers in practice, like for instance working with Alstom or Siemens, telling them, look, if you want to do your risk assessment for your train sensor system, then you could take our procedure as a template, and using fault tree analysis in a specific combination with parametric model checking of Markov chains. It is not a result, a disclaimer, a big important thing. So we do not, it was actually highlighted by the reviewers, so we should really make this clear. We do not say that we managed to prove that the resulting false negative rate is actually below the accepted threshold, and that means that trains can in the future be certified according to this result. We can just say we have a procedure that allows you to do that, and then you need to decide whether the parameters you've used when applying this procedure reflect the reality in your particular setting. Yeah. This is always the key question in certification. Certification applies on a case-by-case basis. And in other cases, certification needs to be redone. Yeah. So, okay. Let me quickly walk you through some definitions. We use often the OD abbreviation for rail obstacle detector. It's nothing else than a sensor system. And we have a lambda OD as the obstacle occurrence rate, the rate how often the obstacle occurs in a particular time unit, for instance hours. And then we have an event obstacle present but undetected. This is our hazard or false negative. And then what we are interested in is the probability of our hazard, P of HOD. And then it's also important to distinguish the probability of a single HOD from the rate, so that this is a different view. So with the rate you get based on a particular obstacle occurrence rate, the rate of the false negative occurring. And this rate, this is subject of our risk quantification, is to be compared with the tolerated or tolerable rate, which in our case was chosen to be 10 to the minus 7 according to feedback from a guy from Siemens as responsible or involved in the certification process for particular such systems. What I'm presenting you in the rest of the talk is I'm giving you an insight into how we constructed the fault tree, in how we estimated some of the error probabilities of some basic events in the fault tree. I'll give a very brief insight into how the stochastic model looks like and how we identified the probability of the hazard. And finally, an idea on what we did to actually push the hazard rate below this threshold level. So as you can of course see, this is a very practical work. So this is just hands-on work for risk assessment engineers in practice. There's from a research point of view, we apply methods. So this is not a presentation of a new method, of course. Yeah. So I don't want to align your expectations. Nevertheless, so in we were not given a particular sensor architecture and implementation. All this is under the hood and was not accessible to us. So we had nothing more than the block diagram I showed you before. Basically something that everyone could do at home. And based on that, sorry for the small font, we identified certain, we split down we analyzed the failure possibilities of that two-channel module that would lead to our hazard. On top is nothing else than the hazard, the false negative. And then there are several domains where faults can result, namely the two channels could provide a contradictory result and the voter doesn't see it. This is a typical proof or verification obligation for such a fault tolerance pattern. Then there could be a systematic voter fault, so independent of whether the channels are consistent or contradictory, the voter could just systematically err. And also in this part of the fault tree, it's basically about there are consistent channels, so they both provide the same result, but it's consistently wrong. Yeah. So this is also something that the voter can't detect, because it has only two channels at hand. Right? And this simultaneous failure can occur in the sensing. Sorry, I would like to point in the sensing component, in the perception component, and also in the communication subsystem within this module. So it's a very straightforward breakdown, as you can see. And everything that happens below there is then detailed for the perception component, which, according to our assumption, is the most complicated, most complex component of these of the sensor system, because in the perception component we assume that there are neural networks, convolutional neural networks used, for instance, to do the obstacle detection, at least in one channel, while the second channel can still be based on conventional techniques like simple camera-based optical edge detection and stuff like that, that has been used for a long time for such things. So and then this is why this simultaneous perception failure, the unsafe failure, breaks down into a fraction which is associated with a neural network based system for obstacle detection, and the other one is associated with a conventional perception system used. Okay, I'm going a little into the details on how we tried to estimate the basic event probability for the perception fault in the case that for the perception fault. That means in that particular case for the neural network based channel, so we tried to figure out what is the residual probability of the neural network not to detect an obstacle when it's there. Yeah. And there's a couple of, this is ongoing work actually, at the point when we wrote this paper, this was ongoing work, which is why the details in our paper are only quite partial. But in the meantime, my co-authors managed to get a more detailed paper accepted. It's in the slides. I can also share the citation for you. The whole neural network is so what we did is we built up a mathematical model of the neural network. So we assume that there is an image database with known obstacles as a subset, and we assume that there can be a metric that gives us information on the equivalence of two images of that database. Yeah, there's a lot of formulas, but essentially it means for two images, we say they are equivalent if that particular metric tells us that they are null connected. So the difference between the metrics for both pictures, so there's no difference between the metric of for both pictures. And then they are in the same equivalence class. We further assume that we have a number I of such equivalence classes, and that the probability of an image drawn from a particular equivalence class is also known, symbolized with pi. And what we then do in order to finally identify the misclassification error probability, or the probability of a false negative of the neural network, is we apply the coupon collector problem. The coupon collector problem basically uses a central random variable which models the number of draws I'd need, draws of images from the database I would need to cover the existing equivalence classes. Yeah. So you would just, in one simulation run, you would constantly draw images from your database, apply it to the neural network, and then stop if the neural network has seen and correctly classified at least one image in each of the distinguished classes, right? And then you get sort of a coverage, yeah. And the coupon collector problem allows you to provide a distribution for this random variable. Because this is not analytically solvable, such problems are typically approached with a Monte Carlo simulation. And this is what has been done before, of course, but this is also applicable here, where you eventually get some probability of, for 5 minutes to go, okay. Okay, I will rush through because this is actually perhaps something that because of the workshop I was wondering whether I could rush through a little more. I think the main result of this slide, which contains quite a number of intricate details, the main message is so we use the coupon collector problem to figure out the probability that the neural network misses one equivalence class, and also incrementally reduce this error probability, this misclassification probability, by adding increasingly many equivalence classes to the original set. So this is a mathematical framework. Yeah, there's currently no big enough database. That's also important to say, which captures enough pictures, but it's straightforward if the train domain starts selecting and collecting such images. eventually we get at least a notion of error probability, an upper bound for this error probability. And what we then need in the fault tree is just to choose an error probability that is bigger than the upper bound. Yeah. So conservatively choose an error probability for the basic event, and this allows us to then go further in the fault tree. So what we did is now we managed to mathematically inform us about the upper bound of that error probability, and we choose a larger one. We do this. We do a similar mathematical reasoning for the other basic events. Also, we use a chi-square test to actually test whether the channels are diverse enough that that their error probabilities are stochastically independent. This is an important check because otherwise the fault tree is invalid. Yeah. So not even important to understand what is on the slide. For a fault tree, it's important that all the basic events are stochastically independent in order for the composition of the fault tree to work properly. That's what we also did. And now you might ask the question, where do we get the information for the top level event? So we encoded all the basic events we prepared the stochastic model of the processing of the sensor system, inserted all the estimated basic event probabilities, and then this is a CTMC, a continuous time Markov chain. It allows us to then get an estimate of the top level event, namely the false negative rate of the module. And because it's a parametric analysis, we can use a range for the basic events probabilities, and then we get a range for the top level event probabilities. That's the key point, really, that we manage. So the model is a template that can be reused in a wide variety of settings. And that already brings me almost to the end of my talk. We managed to then use two of these modules that I've shown and combine our analysis in order to reach below these 10 to the minus 7 tolerated hazard rate. So we actually need basically two such sensor systems in order for current certification requirements to be fulfilled. This is really the key takeaway, I think, for you. So we have a procedure where you can stepwise work towards this goal, achieving the tolerable hazard rate for such a system. Yeah. I've said all this, and again, coming back to at the beginning of my talk, the grade of automation 4 plays no role in this whole thing. Because we tell you, if you have a sensor system somewhere in your garden or in an autonomous train, we tell you how you can achieve a tolerable hazard rate or not achieve it. Thank you very much for the questions.
Thank you. Any questions? Yes.
Yeah, thanks for the talk. Yes. Thanks for the talk. You said this is very applied and you're not proposing a new method, but perhaps can you comment on where are limitations of the existing methods that you used that you had to work around? So what should be improved in the existing methods?
Unfortunately, that's a bad answer. There are no limitations on the existing probabilistic model checking methods that came in our way when we did the analysis, but there are limitations on the ways of how to construct an image database and to select these image equivalence classes. This is discussed in another paper, but also it depends on the practitioners delivering these images, right?
Okay, so this whole pre-processing where you actually did simulation instead of model checking is not because of a limitation in Prism or something?
No.
Okay.
This is something different. That is also hidden. It's a very important question, by the way. So when you see at this Prism model, for instance, we use what we estimated with the Markov chain. With the Monte Carlo analysis, we use it just as a parameter here. So it's basically done outside the model. And then we assume that the parameter is properly estimated, and this gives more confidence in the overall model. Yeah. So this is why I say that was not a problem. Yeah. Oh, sorry. I just wanted to keep eyesight.
That answers my question.
Thank you.
Any more questions?
So I didn't get exactly, so this is methodology, but has it or has it not been applied to, I understood it has not been applied to some kind of real system, you just had a very brief outline. Yeah, can just, so it has not basically, just a sort of method which has not been applied to a real system, right?
It has not been applied to a real system in the sense that Siemens, for instance, asked us to apply it, but we were in touch with Siemens and they confirmed that this should perhaps be the way how to do it if we were asked to certify a train in the near future. And they gave us some numbers for some of the parameters we are using in the fault tree, particularly the tolerable hazard rate. Yeah.
So you also mentioned that there is a paper, follow-up paper on this, so then you have a point there. Yeah.
So this is the
Cyril, can you,
the first one. It's just been included in the Festschrift for Werner Damm. So this is the paper that explains a little more how we construct, how we abstract the neural network using Riemannian manifolds and degenerate metrics on Riemannian manifolds, and further in order to construct the equivalence classes. And then once you have constructed the equivalence classes, then you can work with the Monte Carlo simulation that I've shown to you. But there's a lot more than there is not discussed in the paper. Yeah, of course. If it's allowed.
You said this has been done and you consulted some people from Siemens and so on. Does this mean the model cannot be published, or would this be available?
No, the model unfortunately can be published because I have crafted it, and we were just asking them for the parameters that I was using in the model. And there's no non-disclosure agreement. So if you like, you can have it.
Perfect, thanks.
Yeah.
Okay, let's thank the speaker again. And then the next presentation will be on solving queries for Boolean fault tree logic via quantified set or satisfiability solving. And the speaker will be Stefano Nicoletti from the University of Twente and Radboud University in Nijmegen.
Yeah, thank you very much. As we said, we basically are trying to solve queries for a logic for fault trees via quantified SAT. This is joint work with one student of mine, Cas Salting, and colleagues and supervisors such as Matthias Volk, Moritz Hahn, and Marielle Stuelinga. And I guess I don't have to sell you fault trees because Mario has done the heavy lifting for me. I'll just put the ingredients on the table that I am using. There are numerous variants of fault trees. We consider fault trees as DAGs, right? So they can have shared children. The name is a bit unfortunate. You know, they can be also not trees, not tree-like structure. We call the objective of the failure assessment, in this case, you know, the trivial tree for a PC, at the top level event. And we call what is in between intermediate events, and then we usually refine them through gates. And here we are focusing on static fault trees, which have OR gates, N gates, and K out of N gates. So the failure to be propagated, at least K children out of N must fail. But you can see the K out of N naively as a sort of composition between N's and ORs. But those are the main ingredients that we are focusing on for this presentation. You can perform quantitative analysis, as we saw in the previous presentation, but you can also perform qualitative analysis, which is quite useful because this points out root causes and critical path in the system that you have at hand. And there is a construct that it's usually present in fault tree analysis, which are minimal cut sets, which are basically minimal sets of leaves, such that if they fail, then they cause together the system failure. In this case, just the RAM propagates the failure to the top-level event, or just power plus UPS because they activate the AND gate and consequently the OR gate. Fault trees are great. We have seen that with Mario, of course. They are heavily used. They are required by the Federal Aviation Administration. They are heavily used in the nuclear domain, NASA. There is tool support by isographs, among others, and they are a viable way to perform safety risk assessment on a system. However, when you usually do fault tree analysis, analysis questions are not as flexible as we would want them to be. For example, when you have what-if scenarios in mind, usually you have to retouch the model. And then we also conducted interviews with domain experts in the nuclear domain, and they expressed this kind of desire for more flexible querying on fault trees and more complex querying on fault trees. We would like something like that, right? So we can ask questions conditioned by certain assumptions. For example, what are the minimal cut sets of a given tree, assuming that a certain leaf or a certain subsystem has already failed, or that a certain subsystem is remaining operational because we guarantee it in some other ways. We can ask if the failures of one or more elements are always leading to the failure of the top-level event. Or, would element E always fail if at most or at least some component were to fail, right? So this gives sort of more granularity to what we can actually do in qualitative analysis with respect to fault trees. And in previous work, we did exactly that. We developed a logic, a Boolean logic for fault trees, to enable this construction of such queries. And in there, we provide model checking algorithms to check properties defined in the logic. And we provide model checking algorithms based on the binary decision diagrams. And we also provide a way to construct counterexamples. And this is also kind of a nice selling point for our work, is that when something is not how the assessor expected it to be, we can restitute examples graphically on the tree, showing path or showing, hey, look, you need to add these other elements for the failure to propagate as you would have intended it. And in this paper that we present here, we present actually the first tool support for the analysis of BFL queries. And we wanted to explore a complementary approach based on SAT solving. So what we do is we introduce a translation from a BFL formula to a quantified Boolean formula. And we employ Z3 as our solver of choice. We implement this approach in Python and provide a publicly available artifact. I'll talk briefly about that as well. And then we evaluate our approach on multiple benchmark fault trees. We do have a fault tree in the original paper, which serves as our case study. But we also use a lot more benchmark fault trees from reliability engineering and from railway industry to evaluate the scalability of our artifact. And this is kind of a quick roadmap of what we are going to see, quite literally. We see some queries on the example case study that we have in the previous paper. Just to give you an example of natural language query, BFL query. This is still not quite formal, just to give you an impression of what we can ask. Then I'm going to briefly sketch out syntax and give you an idea of the semantics and the queries that we can do in BFL. I'll pitch you this translation from BFL to quantified Boolean formula. Why do we need it? And then I'll just comment on implementation and some experimental results. So first of all, let's take a look at some colorful pictures. The original paper was in COVID time, so we thought to apply fault tree analysis to a COVID case study. So the top-level event represents an infected worker joining on site. And believe me, we did get criticism for choosing COVID, because this is not a medicine paper, but here we are. Basically, this fault tree represents ways in which an infected worker can join your workplace. On the blue subtree that you see in the middle, you see modes of transmissions that are detailed. In the orange subtree, you see is there a susceptible host that is actually that could be infected with COVID, and then in the purple subtree, you see, okay, is there actually COVID on the workplace? Are there pathogens or infected surfaces or the like? So one might want to ask questions such as, is an object disinfection error always sufficient for the occurrence of the top-level event? You see on the bottom the BFL formula. Or is an infected surface always sufficient for the transmission of COVID, right? So oftentimes when you do a reliability analysis, you focus on only the top-level event. Here we can also focus on different subtrees, give more granularity. Are at least 2 human errors always sufficient for the occurrence of the top-level event? We have this kind of voting construct also for formulae, basically saying, okay, at least 2 out of these formulae have to be satisfied. And then we can, of course, combine it with the usual Booleans and with quantification. We can also return all the minimal cut set to the user. We use the square bracket for the satisfaction set. So what are all the minimal cut set for the top-level event filtered by some kind of event happening, for example, that include the action of non-respecting the outbreak procedures. And then we can also make sure that something exists, of course. So are an infected worker joining the team and a detection error, a minimal cut set for our top-level event. And yeah, this is sort of the expressive power that we are chasing here, that we are going for when we analyze our fault trees. And I'll just present briefly syntax and an idea of semantics. This is the logic. It's tailored on 2 layers. The atomic formulae for BFL are these E, which represent elements in the fault tree, both leaves or intermediate elements. You can, of course, join formulae with the usual Booleans. And then we have constructs such as this one and this one, which we call setting evidence, which is what I was referring basically before. You want to set a certain atom in a formula to a specific value, assuming that something stays operational or that it stays failed. Then we also have an operator to check whether a given assignment on the leaves, so on the status of the leaves being failed or not, is a minimal cut set for a given formula. And then, of course, in the second layer, we can quantify, and then we can check for independence of 2 elements in the tree, so to speak, with the idea that 2 elements are independent when they have not influencing children that influence both the truth value of these 2 elements. And then the semantics is, you can probably imagine it. I mean, if you take a look at the fault tree, it's already kind of a Boolean function. There is in the fault tree literature this structure function, which is exactly what it sounds like. So you are given an assignment, a Boolean assignment on the status of the leaves and an element in the tree. And then basically this function tells you, yes, this element is reached with this assignment on the leaves. No, it isn't. And you can see a really quick example on the trivial model that we had before. Of course, the assignment 100 is sufficient to reach the top-level event, so our atomic formula is satisfied. Picture this, and then we basically extend this sort of idea for all the other constructs that we have in the syntax. I'm not going to bother you with full semantics. We do distinguish between different queries. That also trickles down to the implementation of the artifact. We have query type 1, so we give a Boolean assignment on the leaves and the model, and we ask usual model checking problem, hey, is the formula layer 1 satisfied with this assignment and with this model? Query type 2 is formulae on the second layer, so we have only the tree, and then we basically ask whether there is such an assignment such that the formula is satisfied, or for all the possible assignments on the leaf, is that formula satisfied? We call it query type 2. And then query type 3 is a satisfaction set for formula of layer 1. translated in fault tree terms, sets of satisfying assignments on the leaves such that the formula is satisfied. And I'll briefly pitch you the idea on translating BFL to QBF. So there are, of course, 3 fundamental steps in this process. We only translate needed parts of the fault tree model that ends up in the formula. We then translate subsequent first layer and second layer BFL formulae. And as you can probably imagine, there is a direct comparison between what you can see in the image and what is written there. So fault trees are already kind of Boolean functions, so there's not much surprise there when you translate the fault tree to QBF. You don't actually need quantifiers. Of course, you can have at least and at most defined in terms of ends and ors, but since we rely on Z3 at the end, there is better support there in the artifact to handle these kind of functions. The idea behind translating layer 1 and layer 2 BFL to QBF is that we need quantifiers due to the semantics of some operators in BFL. I mean, second layer, you can imagine yourself, right? You saw quantifiers. But for example, also for minimal cut set, we do need existential quantifier because we want to guarantee that there is not such an assignment, which is a subset of an assignment that we already give, that satisfies still the formula. So we have also a quantification hidden in some operator there. And then, of course, we define a recursive translation that preserves the meaning that we originally intended in the semantics of the original logic for both layer formulae. If you're curious about symbols, mathematics, proofs, you can find those in the paper. I'm just giving you the rough idea here. Yeah, and then I'll finish by talking briefly about the implementation and the experiments. Here you can go to the Zenodo repository to take a look at our artifact. Documentation is there. The basics are that the artifact again is implemented in Python, uses the Z3 solver as a backend for the solving. The entry point is our run BFL Python file. Simply takes a bf.bfl file as an input, where you basically specify the fault tree that you have at hand with the Galileo textual format, which is one of the industry standard for specifying fault trees in textual format, plus some BFL properties. In the docs, we have instructions on how to specify properties in the BFL kind of format, but we have a parser for basically what you saw in the text specifying properties. It's all pretty simple, and we do check our experiments and our properties for the original fault tree that we have. I showed you some of these properties. Maybe you will recognize them in the first slides in natural language. And then all of these come out as expected by conducting the analysis by hand. But also we conduct 2 more experiments to test for runtime, memory consumption, and scalability. This is quite a small fault tree, and I come from the Netherlands. We are a very fan of fault trees because that's actually what keeps our feet dry, because the storm surge barrier that protects us from storms, it's actually using fault tree analysis. So we want this to scale. So we devised the first experiment, which is the single fault tree experiment. We basically take these properties, and not only we check them, we just analyze them for time of checking and memory consumption. And you see the graphs. You see on the one on the left the time over length of the QBF, or the already translated QBF formula, and then on the right, same for memory consumption. Key takeaway, there is a suggestion of a linear correlation between length of the QBF formula and the time to check it. There is an outlier in Q3, which is sort of explainable because what we are asking here is to basically return all the cut sets that satisfy the top-level event without requiring minimality, right? So this can grow and can be computationally challenging. Also, there is a suggestion of linear increase in memory consumptions. Admittedly, we have not many data points, so this can be explored further. We also devise a multi-fault tree experiments, especially checking scalability. We have 7 fault trees from reliability benchmarks. They are usually used, so these fault trees are from real-life case study in the engineering community for railway locks, basically, and more complex. And you can see Q11 and Q12, we sort of try to specify the same property for every fault tree. The first one is taking basically the minimal cut set for the root node, filtered by some events. And then in the second one, Q12, we ask, is there an assignment such that top level event fails and some leaves have a set value? And I mean, as you can probably imagine, already taking a look at the graph, the type of property that one specifies has a great impact on runtime and memory. You see that for the time of Q11 and the memory of Q11, which are the blue and the red point, those values tell a completely different story than Q12, right? Because it's Q12, it's admittedly more simple because you're just asking for one satisfying assignment, of course. And then the second finding is that the structure of the fault tree, more than anything, has more impact on the runtime and memory than the number of fault tree elements. If you take a look at, for example, the edges of the fault tree, or at the ISP, EDF, and ELF fault tree, those are the fault tree that are more intertwined, so they resemble more of a directed graph than actually a tree in the structure. And then they have more of AND gates and voting gates than the other trees where the OR gate is prevalent. So it's not so much about the number of nodes, but the structure of the fault tree itself that impacts this evaluation. So in conclusion, we just saw the first tool to support analysis of BFL queries. We tried implementation with a complementary approach other than BDDs, which is SAT solving. We have a translation from BFL to a quantified Boolean formula because we need quantification. And then we have an implemented artifact in Python publicly available, and we saw some graphs evaluating this approach. For future work, we want to work in 3 directions. Develop an implementation based on BDD, so we don't have just a pseudocode in our paper, but we actually can perform concrete comparison between these approaches. We want to further investigate our restricted translation, and this was suggested by one of the reviewers, thanks for the note, that only takes a fragment of BFL without quantifier. That can also be interesting to evaluate on only SAT solving. And then maybe conducting BFL user studies to gain further insights. And then, of course, when we do the comparison, we might want to use fuzzing for generating automatic fault trees and automatic properties to keep the comparison more fair and then more scalable. Not me hand-picking properties and then creating files by hand. That would be nice. That's all I have for you today. Thank you for listening, and please do get in touch if any of this sounds interesting to you. I'm happy to take questions.
Thanks, Stefano. I have a question about this BFL logic
Yes.
that you showed us. You had this, there. So there you said observe that an event is true or false by setting it to 0.
Yeah.
And in your examples, it seems you only do this for basic events.
Yes.
Can I do this for, I don't know, a gate somewhere in between and then figure out what basic events have to fail or could fail for that?
Now you're asking the interesting questions. So I used only BEs because there is an asterisk in which kind of intermediate events we can do this for. We can do that if the intermediate event is the root of a module in the fault tree, which is basically a self-contained subtree, right? And if none of the children are present in other formulae. In this way, we can sort of prune that subtree, and the easy way to do this, it's maybe the ugly way, but for now, this is the restriction because we basically, if those 2 conditions are met, we can prune the subtree and treat the intermediate events as a basic event for all intents and purposes. So yes, asterisk.
Okay, thanks.
So, maybe it's a strange question since everybody anyways uses Z3, but why Z3? Why not, CZ4, yikes, just for, or CZ5, or I guess now?
Yes, so the main commodity that we found is that Z3 has very nice Python APIs. So we sort of did already the parsing for the BFL and the original file in Python. So this tied very nicely in the framework that we built, and also you can sort of keep some certain values fixed and let Z3 recompute a satisfying assignment starting from a certain value, which of course maps very nicely to us wanting to have a fixed BE or root of a module in a certain configuration. So, thank you.
I also have a quick question. Again, you said publicly available. Under what license?
MIT.
Thanks.
I'm ready.
Yeah, because you cannot use it if there's no...
Yeah, no, MIT.
So even if it's out there,
Yeah, thanks for a very nice talk. How do you, perhaps I was missing it, are you planning to include also probability in the next, I don't know, steps of your work?
Yeah, we do already have a paper accepted at FM, which basically extends this logic with probability, discrete probabilities, mind you, not yet failure rates, but that's already out there. And or also for that we have pseudocode algorithms for sort of building up on the BDD's method that we had in the original paper mentioned here. One of the desiderata that we have in the future is, of course, also extend this and or the BDD framework implementation to probabilities and to handling probabilities as well. Yeah.
Does this extension, or does the other paper already include some sort of notational primitive, like the voting, to pick out the most critical cut set or something like that?
So yeah, basically what we have in the other logic, it's a superset of this. So yeah, anything you can specify with this, you can with the new logic, the probabilistic logic. And also, I don't have a slide, but in the derived operator, you saw that this voting operator here, that we have, and we still have in the next iteration. We just add a layer for metric computation and bounded probabilities and this sort of machinery.
Yeah, very nice. Is there a company using it, to ask a last short question?
No, not yet, but we are sort of at least trying to integrate all of this in the Storm probabilistic model checker. Matthias Volk, the third author, is one maintainer of the Storm model checker. So we are sort of trying to push that into the model checker as well. Thanks.
The third talk in this session will be by Raul Lopez on symbolic analysis by using folding narrowing with irreducibility and SMT constraints.
Okay, thank you. So I'm starting with this presentation. This is the outline. First we will have an introduction. Then I have prepared a narrowing example so we can understand a bit what narrowing does. Then we have the running example, which is the base of the running example is coming from an example which was presented here last year. Actually, some of the authors are here present. Then we are seeing our folding canonical narrowing with irreducibility and SMT constraints. I have some execution examples and finally the conclusions. So let's start. Okay, rewriting with satisfiability modular theories has been recently used to analyze system modeled using parametric time automata. Okay, we are no experts on parametric time automatas, but we have used those examples to show the potential of our algorithm. Okay, so in this work, we propose to generate a finite state graph, not by rewriting with SMT, but by narrowing with SMT. Narrowing with SMT allows a greater generalization. For example, an infinite number of initial states may be represented by a finite number of states with variables, and not only the SMT variables. Everything can be a variable in narrowing. An infinite state graph from an initial state may also be represented by a finite state graph from another initial state with variables. We use graph search pruning techniques via irreducible terms, which come from previous work, and SMT constraints on conditional rules. Okay, so why extend narrowing algorithms? Our implementation of folding SMT canonical narrowing really generalized, as I said, previous techniques for symbolic analysis as rewriting. With our symbolic reachability algorithm, not only numeric variables can be found in the initial and final states, but variables of other types are also allowed. Now, if we check a property using reachability problems with variables, then we are checking it for all possible instances of a problem, okay? So if we have a generic initial state and a generic final state, and we verified a property using narrowing, then all instances are covered. For our algorithms and for the experiments, we use the mod system. It's a system and a language based on rewriting logic, so it uses both rewriting rules and equation. And it is capable of handling many forms of symbolic reasonings, such unification, narrowing, most general variant unifiers, and SMT. Currently, it's used in a wide spectrum of areas, like security protocol analysis. Santiago, the co-author of this work, does that a lot. Then through model checking, partial evaluation, theorem proving. But there are some limitations of narrowing in mod, which can be, for example, handling conditional theories or handling SMT constraints, irreducibility constraints, etc. And we have made some extensions of narrowing in mod. The first one was to add the canonical narrowing to the standard algorithm. So we used irreducibility constraints to make a pruning of the tree and reduce the search space. Then we had the addition of SMT constraints. So we handle conditional theories, which contains SMT constraints in the conditions. And then in this one, we combined those two articles into one and use it to define a lot of experiments and some practice. And also we have in ICFEM 2022 another line, let's see it like that, in which we handle conditional rewrite theories, but not only with SMT in conditions, but with variant conditions. And now in this work, we are using the canonical narrowing with SMT constraints, but now we have the folding narrowing. Okay, so the folding narrowing what does is folding the search space, so we can, well, we see later. Okay, but let's see first an example so we can understand how narrowing works. This example is just a basic coffee machine, okay? I will not... sorry. I will not explain in detail because I don't have any much time, But basically, we have two rules, okay? They model the transitions of the system. So in the first one, we can just take $1 and buy a coffee. And in the second one, we can buy an apple, and a quarter of $1 is left over. Then we have some equations that are just equalities. The first one is an equation of change. 4/4 of $1 become $1. And then we have 3 idempotency equations, one for each symbol, okay, but not for the quarter, because we already have a equation saying that 4/4 of $1 become $1. So we have idempotence for apples, coffees, and dollars. It's a little counterintuitive to have idempotence on money, but it's just for showing how narrowing works. Okay. This is an example of how we can visualize an execution of narrowing. So imagine we have an initial state M1, which is of type money, and then we have several transitions that we can do. Then we will have several branches on the search space, okay? So some of them are not deployed here because of the space of the slide. But we are interested in this one, the red one, okay? And we can see it with some detail. So we have the initial state, M1, and then we want to do the first step, and that could be applying the second rule to buy an apple. Then we have a substitution for the variable M1, which says M1 becomes $1 and another variable M2 of type money. And then we have another substitution for the variable of the left-hand side of the rule, so they can both unify M1 and the left-hand side of the rule. We rename it because of mod purposes, so M becomes W1, and it becomes $, and M2. Then, if you see in detail, we have now $2 in the left-hand side of the rule, okay? We have $1 and the dollar of the substitution, so we have $2 and M2, and here M1 is only $1. But because of the idempotence equation, $2 become 1, so these $2 will become 1 and unify with the M1 variable, okay? Now we can make the step, take the step, sorry, and we go to this state. Since M1 is $, M2, we get $1, an apple, a quarter left over, and M2. We can go to the next step, and it's pretty the same, okay? So now we apply the first rule to buy a coffee. Again, we have the 2 substitution, and again, we use the idempotence dollar equation, and we go to the third step. In the third step, we apply again the second rule to buy an apple, and again, we have the 2 substitution, we apply the idempotence dollar equation, and this is a narrowing trace, okay? A normal narrowing trace. What happens here? In the first step, we use the second rule, but we could also have used the first rule, so that would be another different trace, and that happens in every step. So in the end, we have something like that, like we saw before, like a big tree with a big search tree, which actually in this example is infinite, since we are using a generic variable M1, and the system can always introduce a new variable of type money. Now we have the running example. As I said, this is coming from a paper presented here last year. So basically, it's a coffee machine presented as a PTA. First of all, we have the idle state, and the system can be there for a arbitrary time. When the user presses the B start button, the counters x1 and x2 are reset or initialized. And we go to the state add sugar. In this transition is modeled in mod with something like that, okay? It's a conditional rule. This is not the original rule, okay? It's slightly modified so we can use it with narrowing, but the original rule is quite similar. We have the state, the two counters, and the parameters, and we go from idle state to add sugar state with a new value for the counters and the same parameters, and with the SMT conditions modeling the initialization of counters and this invariant. So the system will be here as long as the invariant holds. And in this time, the user can use the button B sugar to add some sugar. If x1 is greater or equal than the parameter p1, and the counter is reset. After p2 time, p2 time after the B start button was pressed by the user, a cup is delivered, and we go to the preparing coffee state, and we will be there as long as x2 is less or equal than p3, so that's a new invariant. And finally, after p3 time, after the user presses the B start button, the system delivers a coffee. Sorry, this one. The system delivers a coffee, and the x1 counter is reset again. We go to the final state, done, and we will be there 10 unit times, unless the user presses again the B start button, and we start again in the add sugar state. Now, our extended or modified version of the PTA, I don't know if someone here is an expert on PTAs, and we are not sure that this could be actually considered as a PTA, but it's just an example to show what we can do. So now we add two new variables. The first one, C, will be a counter of coffees. So now we have a count of the coffees prepared. And the second one is just like in the example before, the money. So now we have money. And actually, in the idle state, we have a new transition, B quarter, what we call B quarter, but it's not really a button. It's just that the user can introduce quarters of a dollar to the total amount of money. And to go from idle to add sugar, we need 3/4 of a dollar. So a coffee costs 3/4 of a dollar. The same happens when we want to go from done to add, this one is from idle to add sugar. And the same happens when we want to go from done to add sugar. If there are 3/4 of a dollar left, we can make another coffee. And from preparing coffee to done, we add a coffee to the counter of coffees prepared. So as you can see, the rule is quite similar, but now we have here the money and the counter of coffees. And in this transition, the B-star transition, we can see how we have at least 3/4 of a dollar and the rest of the money. And to take the step, we take out the 3/4 of a dollar. Now, folding or narrowing in mod. Mm-hmm.
Clarification. Okay. Some simple question for this clarification to understand example. So I guess that basically this M contains multiset of Q.
Which?
There's the new components contain multiset of these Qs, right? So,
Yes.
so is there any reason that you do not use integer?
We did not use what?
Integer theory of integer to encode the number of Q. So
Of integer. Yeah.
yeah.
Because
So just curious. Then there would be pure.
yes. So sorry. Yes.
SMT.
That's a good question because I missed that. So the idea is that we also wanted to have equations in this system. So by having quarters of a dollar, we can also have the equation that we saw before, in which 4/4 of a dollar become a dollar. So we can have change of money in that way, and that's only the reason. Okay, so now to follow narrowing in mod, we have the data structure which was a tree, and now it has to become a graph since we are folding the tree. The data structures of the nodes must also be modified to include new information, for example, the node on which it's fold or not. And we have to add new functions to determine when a node falls into another one. And it should be checked bidirectionally for nodes of the same depth. So a node which is on the same depth of other nodes, they can fold bidirectionally, okay? So if one doesn't fold into the other, we have to check it the other way. We make several calls to mod's SNT solver to determine if the necessary implications are satisfied. And actually, in a future, I'd like to maybe try the QMean version of mods, so we can use other SMT solvers, because we are only using now the JISIS2, I think is the one mods uses. So when does a node fall into another? Nodes are now a triple composed by a term, an SMT constraint, and a list of irreducibility terms. And a node falls into another node if the first node is an instant, or the first term of the node is an instant of the second term. That means that exists a substitution, and applying that substitution to the second term and modulo equation and actions, it becomes T1. The second condition is that implication, the negation of that implication is unsatisfiable. That means that we are checking the validity of the implication. And the last condition is that the terms in the term in which we apply the substitution, T2, so the terms in the irreducibility list of 2 must be EV irreducible. That means modulo equation and axioms. Some example of executions. I don't know how I'm going with time. I'm fine. Yeah. Okay. So, for example, this one is, I think it's quite similar to the one used in the original work, but using narrowing. So we can ask, is there a way to get from a generic idle state to the done state by buying at least 3 coffees and with at least $2 left over? Note that we can use at least because we are using a variable next to the $2 and a variable next to the 3 coffees. So it is at least, not exactly 3 coffees and $2. And if we don't use folding, the execution will be stuck in an infinite calculation. Why that happens? Okay, that happens because if you check the model, the system can always go in one of the traces from the state done to the state at sugar by B start, by transition B start. So there is a loop, and the narrowing without folding won't be able to terminate. But if we use folding, folding will achieve something similar to the system model. So it's folded, and then it can find a solution. So the answer to the question is yes, we can do it. Another question, is there a way to get from the idle state to the done state by giving any values to the counters, the parameters, money, and coffee? So it's the same, it's the same as as before, but now everything is a variable. So this is just like going from a generic, completely generic initial state to a completely generic final state. And again, a solution is found. So the answer is yes. And the last one, what if we start with exactly $2 in the idle state? Then we will have two different solutions. Why? Because the first one will be that we buy 1 coffee and $1.25 left over, and the second one, with the first one, we go from done to idle directly, and the second one, there will be only a loop, and then we buy 2 coffees and $0.25 left over. And the conclusions. So we have developed a novel folding SMT canonical narrowing, which extends our previous works. These narrowing techniques use both irreducibility constraints and SMT constraints. The SMT constraints will be specified within the conditional rules. And the irreducibility constraints will help to reduce the width of the search tree when using rewriting theories with complex varying unification. In this case, the impact of canonical narrowing, that is the impact of irreducibility constraints, was not too much, but in cases in which we have a lot of equations, the difference between standard and canonical narrowing is huge. Folding can considerably reduce the computing time, or as we saw in examples, even ensure termination when the search tree can be fully folded into a finite search graph. And we have used the algorithm to analyze a PTA vending machine that was specified and analyzed with rewriting modulo SMT. We have also extended the example with new features to further demonstrate the symbolic potential of the algorithm. And we think narrowing goes a step further at the symbolic level, allowing us to use variables beyond SMT in the initial terms. And that's all. You can find both the code and the implementation of the algorithm in this link. And yeah, that's all.
I have two questions. First, what makes you believe, you mentioned it, that the parameterized timed automaton is not is not one actually, and the second one is perhaps
It's not,
also
sorry?
is not a, so the automaton you said the automaton you have in front of you is perhaps not actually a parameterized time. Okay, yeah. What is the reason why it is not a timed automaton?
No. I said I don't really know, since I'm no expert in parametric time automata. I don't know which are the restriction
I see.
to consider a parametric time automata as that.
Well, I mean, you see here all the new stuff, right? So because you know in time automata, you can only the clocks can only be set to 0, right? So everything that's new here, you know, I mean, it's not part of the definition of an automata or time automata. So
Okay.
you know, it's m is assigned to m minus q to q. I mean,
Yeah.
it's not just you know.
Second question. Thanks. That's what I was wondering. Okay, and the second one is maybe I was missing the misunderstanding the folding and the role of the folding. But if you hide non-termination cases, is this folding then sound?
Yes, I don't really know the theoretical implications, but the answer is yes.
Well, I mean, you know, you do exhaustive state analysis if you find the same state again or something like that. So then, well, okay. So then maybe since I'm here, I can have also some questions. I got the mic. So I guess, yeah, I was just confused with the first example, right? That, you know, $1 became $2 or vice versa. But that, of course, doesn't apply here, right? So, or quarters and so on. The second example. But the main issue is, which I noticed that, you know, in the first example was a little bit artificial because you used the global rules. I mean, so, you know, the left-hand side have to somehow, seems like it catches the entire state.
You mean this one?
Yeah. So you see, normally, I mean, normal example would just be by C would be $, goes to a coffee, right? So without the M and without, you know, these, you know,
Yes.
angled brackets, right? So yeah, can you tell me more about that? Is this necessary? I mean, your approach only works on these global rules.
No, I mean, if we remove the variable from the rules, we would be doing rewriting.
Yeah.
So we could use narrowing, but the solution will be equivalent to that with rewriting. So the idea is to have something a bit more generic.
Okay, so you need that in the rules to be able to do this narrowing.
Yes.
Sure. Okay.
I mean,
then it's a little bit less valuable, right? Because then you have to first fake the rules in some sense.
Yes and no. I mean, it's just a modification of the model, so you can have something more generic.
Yeah, but as an engineer, I mean, you know, as a developer system, I would just write, you know, $, goes to C, right? I mean,
yeah, but yeah. Shall I?
Some comments. It's necessary because narrowing-based analysis will not be complete if the rule is not topmost. So should be topmost, otherwise incomplete. And then another question. Some question is that it seems that narrowing should not involve any SMT variable, right? So somehow you assume that states is separated.
Yes.
Some parties only involve narrowing and some parties only involve
yes.
SMT. Do you consider some mixture? Or
Mix them.
Yeah, mixing some SMT constraint.
Yes, I mean,
narrowing.
Not.
Yeah, just
we can't handle that now, but we are thinking about some ways of handling it. So yeah, maybe we can do it. Like we have it on the list of future work.
I guess that for the next example of that involves a number of different components of timed automaton, right? So in that case, each timed automaton component involves some clock variable and then considering arbitrary number of components should involve mixed data structure containing both SMT variable and narrowing is. So might be more interesting.
We think it's quite interesting that approach, and we really thought about that, and we will think about that much more because as you said, it's really interesting and could be way useful.
Any more questions before lunch? Okay, then let's thank the speaker again. Just remark, please add a license file to your GitHub repo, because otherwise people can't use your code legally, actually. I see this, like, I think also statistically, like 30% forget to add a license file, but this means that no one is really allowed to use your code, so you need to remember. So then we have a lunch break now until 2, and I will be back a bit before, so I'll try my laptop, and we have no other speakers who are here in person, so I'm the only one who needs to try out the projector.
There's an interesting talk about medical devices as well, remotely.
Yes, we have a remote talk, but yeah, I assume that they will figure out how to connect. That's not something we can encourage or help with, so it just has to be done.
Okay, good. So, good afternoon. So, welcome to the afternoon session. And there will be 2 talks, followed by a discussion session, I guess. And then first talk is, does Rust Spark Joy safe bindings from Rust to Spark apply to the BBQ library? Will be presented by Cyril.
Welcome. I hope you all had a good lunch. I present the work of the master student Aysat Maiga with the great title, Does Rust Spark Joy? What do we need for these 2 languages combined to spark joy? We want to achieve a safe language binding if we call from Rust code into Spark code, because both languages are very well known to provide a lot of memory safety guarantees. But what happens if we call code in one language from another? So we all know that C and C++ code is responsible for tons of security and safety problems because of memory errors. And how can we call code from one language to another? There is no way then to go through the lowest common denominator. So if we are at the high level of Rust with memory safety, we want to call Spark code, which also has certain provable guarantees and safety. We have to go through this ugly valley of low-level C code bindings, and we lose the memory safety. So the interface through which we do this is called Foreign Function Interface, FFI, and you have to know a lot of conventions and rules to write the code in the right way. So our question was, how can we derive a set of best practices between the 2 languages, Rust and Spark, which are safe, but the combination is not safe if you're not careful. And so we applied this to a real library and also to a number of small experiments and derived a set of recommendations. It's not yet an automated tool, but maybe in the future it might become one. So memory safety is a big problem, and using this foreign function interface brings it back, even from a safe language. So if we have the start of an execution with memory protection in Rust, we call code in C, we might lose this memory safety, and safety might get corrupted, and then if we go back, we can actually exploit this at the Rust level again, because the assumptions that the Rust compiler and runtime environment make are no longer valid at the level of C, unless you also obey this. So you have to trust the code that you call, but the code that you call also has to adhere to a lot of conventions to keep the safety guarantees from the caller. Now, what are these 2 languages, Rust and Spark? Maybe you've heard of them. Rust is quite a modern programming languages that has memory safety if we don't use unsafe code at the C level. Spark is a dialect of Ada, which has been around for a long time. And it's very small here, this table. Both languages are amongst the most energy and time efficient languages in the world. Only C and C++ are competitive, and also among the most memory efficient languages. Compare this, for example, to JavaScript, which is very popular, which is like 50 times less efficient in some ways, or at least 5 times more energy hungry. So for embedded software, you still need those languages that maybe students today don't like so much, but they get the job done. And one of the key concepts in Rust and Spark are ownership. Now the image is again very small, but just to show you the key point, when you have a reference, the reference can apply to a whole tree of objects. Now we can have a reference considered to be shared, in which case we can share this with other parts of the program, and they are only allowed to have read-only access. The mutable part of an object, the mutable reference, can only be owned by one function or thread at a time. So if we want to change data, we're only allowed to do this through the owned reference, and any indirect reference is read-only. we can also borrow a reference, we can pass the ownership to someone else, and then our access becomes read-only. And in this way, we have a lot of guarantees when we reason about the program. And if we deviate from this safety, if we call code in C, for example, we must actually be aware how this is implemented. Otherwise, you cannot do this safely. So we must know the invariance of this borrowing mechanism and ownership. Otherwise, the whole assumptions will no longer be valid. The same with Spark. The biggest change in Ada was actually this addition of Rust-style ownership in 2019, so that's quite recent. Ada always had a very strong type system otherwise, so it has a much more fine-grained type system than most programming languages. It also has to, support for certain mathematical proofs that you can ensure that runtime exceptions don't happen. You can't prove that the result it computes is always right, but you can prove in many cases the absence of runtime exceptions. Now, we want to be able to call from Rust to Spark. That's the goal, if you remember. And for this, we want to be able to derive recommendations, at least for the majority of data types. So the first step was to look at what data types are out there. Rust has quite a fair amount of open source code already, especially in the so-called crates library. And we looked at 14 code bases, and we found that more than half are numbers, about a quarter are references, then a bit more than 10% are enumerations, and then the rest are other types. So we basically can see that by focusing on the top three, and numbers are primitive types, so that's easier. So by handling references and structs, we can handle a large part of the language, and then arrays are included in others, and are of course also important. With Spark, we can, in this way, cover an even bigger percentage, because structs and references are a bigger percentage, but because there is almost no open source code in Ada, we had a very small code base. So this statistic is perhaps not representative of code in general, because almost no code is open source in Ada. We looked at a number of selected examples first that we designed to just try out different cases of passing data from one language to another. Because there's not so much time, I skipped this. You can read about this in the paper. What I would like to explain you is the main case study, which is the barbecue library, which is a bipartite buffer, hence the BB in barbecue. And it implements a queue, but it has a limited size of the buffer. And the idea is that this queue can be used by multiple threads at the same time, and we can read as long as there is data, and we can write as long as there is space. Of course, we could always implement this using locks, but then it would be relatively inefficient. So the challenge here is that we can implement this without locks, but that we use atomic variables in the right way at the right place and still be thread safe. And the way this works is that we have a read and a write pointer in the circular buffer as shown in the top half of the image. So this is the data. We can read from here up to this point until the data is exhausted, and we can write from here until there is no space. And you can see at the bottom half of the image that if we write data, we append this and we wrap around the end of the buffer. And at the same time, we remember how much we've already consumed, so the different limits, they move accordingly. Now the challenges are that we have to implement this correctly by knowing how the buffers are encoded in the first place, and also how this atomic access is managed. Now, how do we implement buffers if we want to be safe? We cannot do this like in C. In C, the buffer doesn't know its size. It's managed by the programmer. And that's why we have so many mistakes, and we always have buffer overruns and security problems. So if you want to do this safely, the language itself has to know the size of the buffer. And therefore, it has to allocate, of course, space for the size, and the layout on the stack or heap are not the same, because we now have a value for the size and a value for the data. So for example, here you can see there is a size information and the number of elements that you can have as a limit. And Barbecue was also chosen because it's the only library that actually exists in both programming languages. So there is an official version in both languages, and then there's one that was adapted to be able to use this foreign function interface. So this was adapted before our work, and therefore it is sort of a realistic case study in that we didn't write our own code and then try to make it work, but we tried to make this work with code that was already written for the function interface for access using C, not between these two languages. And what's also interesting is that the memory block has to be contiguous, so there are many assumptions about this particular data structure, which makes it among the more complex libraries that you can use in an embedded system. So we have this lock-free access, these assumptions about how the memory is allocated. So we think if we can do this one, we can do a lot of other programs as well. Here we can see a bit how the two languages work together. So we have the user of the buffer, which is Rust, and it accesses data through what's called a grant. A grant is a wrapper around read and write access, and internally then it can access the low-level memory. And the memory itself is handled by the Spark implementation. So it implements the atomic variables to handle all the counters for the positions and the memory buffer itself. Now, before we address this big problem, we looked at smaller examples just to see how the different types actually work, because it would have been quite a big step to go straight into Barbecue. So we looked at the different types of parameter handover. For example, there are copy types, there are reference types, and ISATA studied the documentation and the layout, and then from this derived the exact declaration how this has to be done. So you always have to declare this as a C data type, both in Rust and in Spark, to be able to go through this lowest common denominator and to really specify how the memory is laid out. So you go to Rust, you read how this looks like in Rust, then you design a C struct that has the exact memory layout on the Rust side, so you can pass the argument, and on the Spark side, you again use the same C struct to receive the argument. And then you also have to deal with ownership, etc. So we did this for the different data types, and what's interesting here is that you actually have to give up some of the safety. You cannot use some of the safety features that you normally have in Rust, like ownership. This is because once the data goes out of scope of the first language, the compiler, the assumptions of the compiler are no longer valid, because you can't know what happens when it goes outside of your control. And the assumptions in the runtime environment are no longer valid either. So you want to minimize the amount of code that is handled through this unsafe interface, but you have to let go. You can no longer use the ownership guarantees that people rely on so much normally if they write code only inside the language. So here we can see a simple example just to show how a string looks like. So again, the string has bounds, which it doesn't have in C. In C, it's up to you to know where the string is and how many characters it has. But here, we have two integers to denote the bounds. And then we have the data itself, which is an array of character, a buffer of characters. So that is the same. So we have the C string wrapped in a data structure that mirrors what's in Ada, or the same in Rust too. So in Rust it's similar, except that we have the bounds encoded a bit differently, but it's the same principle. We have information about the size of the string here by the number of elements, and then the low-level string is again a buffer of C characters. Now both of these data structures cannot be exported directly, so we have to what's called forget about it here. So this forgetting means that we let go of all the safety guarantees, and now we have to implement the handover correctly so that the safety guarantees, which are no longer done at the language level, are done at the code level instead. And then we go back to barbecue. So again, we have to encode the data structure. We also have to handle these grants. We cannot pass them to the other language, so we have to temporarily suspend the safety mechanisms for the data that is passed, or ensure that at the source language, and then the actual change is implemented in the target language, which is Spark. Here we can see how the memory is laid out. So the two sides are not completely up to scale, but again, we have metadata that has to be mapped to correspond to each other. So it's a copy of the metadata, but it has to have the same size limitations. And then a pointer to the buffer, which is shared. And atomicity has to be ensured, and the right memory layout has to be ensured. So these are maybe the most important part about these good foreign function interface FFI design principles. So the layout and behavior of the code have to be ensured by writing the code in the right way, because the runtime environment no longer guarantees it. And figuring this out was the task of the student. So there is unfortunately not so good documentation about how to do this step by step. Instead, you have to look at the documentation of the language itself and derive this. So there was a gap in how far this description goes. It basically ends at the foreign function interface level, but it doesn't really carry you through all the way. You can also not use high-level references, because those have the ownership principle, so you have to go back to low-level pointer, and a small mistake can break the memory safety. So we used a memory checking tool, Valgrind, to ensure that the code is actually still correct, at least as far as the test cases go. Here we can also see how this is done for different data types. So we cannot use strings that can be borrowed and that exist only once physically, but we have to go to these low-level strings where ownership is hidden by the user and memory is managed by the programmer. Certain parts of the memory are also not straightforward to access, and certain concepts are not exactly the same between Rust and Spark. So for example, the ownership is a bit less powerful and flexible, but the memory allocation is a bit more powerful in Spark. So again, you have to kind of find the lowest common denominator and try to express everything as C code. Furthermore, both languages have exceptions, which are a great way to manage error states. Unfortunately, you cannot use exceptions across the language boundary. So this would violate these good citizen behaviors for the foreign function interface. The reason is that Spark doesn't directly use exceptions, and the state at which you would end up when propagating exception through the language boundary is not defined. So we would have unexpected changes in the state of the inner language, and they would then not propagate correctly back up to the outer language, at least not unless the runtime interfaces and runtime environments are changed, because we go through C at some point where we have no exceptions, and the exceptions would also not be implemented in the same way. I mean, Spark is basically an error code. So we have to make sure that we don't throw exceptions at the lower language. So our conclusion is it's feasible to write memory safe code when calling from Rust to Spark. The student also thinks it's feasible to create an automated tool, but that would be probably several years of effort. But the documentation really doesn't help you. So it took a few months to figure out all the details. We did this by examples, and you can see the examples in the paper. There are about 8 or 9 representative cases for different types of arguments and usages which we implemented in each language. And if you follow the way that the languages work at the C interface layer, you can preserve consistency. But then if there is an error or exception, then you're again faced with additional challenges. So it's very easy to fool the compiler and make this unsafe, but our goal was, of course, to make it safe. We did our best, and we used the memory safety checking tool to ensure that none of the tests reported any memory safety violations. And I think early in the work there were 1 or 2, and then I thought to fix the bug, so now the code all passes these safety checks. This is all done through the C interface and the application binary interface in C, so that's why it's called ABI there. And you also have to use the right compiler flags to avoid any optimization that might again break the safety. So for example, you can't have name mangling. You have to use this C representation internally, that there is no change in the memory layout, and certain other features in each language have to be used so that the code really comes out the way you expect it to come out, so that the compiler doesn't make any improvements that would then break things again. Thank you for your attention, and please ask if you have any questions. I'm trying the best I can. So unfortunately, Isat is not here who could answer all the questions, but I'll try.
Any questions?
Does this work? Yes. You mentioned that it's not possible to move ownership from Rust to Spark. And like the way I understand this FFI, like it's not possible because the FFI doesn't allow you to write like &mut something into the specification of the external function, right? But doesn't this still mean that you could like logically move ownership around and just like convert the pointer unsafely to a raw pointer and then on the other side convert it back?
Yes, that's what we kind of do. So it's also that we only call code in Spark from Rust, and there is currently no callback or going the other direction. So this helps a bit. Some of the reasons why we can't just pass ownership is that in Rust you can also use array slices, so subsets of an array, because Rust thinks it owns everything. So if you were to pass an array slice to Spark, then Rust would think it owns the rest, but on Spark you can only get the whole array. So this is one example how the assumptions could easily break because the languages are not exactly the same. And originally we were hoping to do both directions, but it was actually challenging enough to do one, and then the other direction is left to future work. So maybe the student will someday do a PhD thesis, then we could do the opposite direction, but this is still open.
Yeah. Could you use this as a basis for a wrapper Spark in Rust? I mean, you rely on the wrapper C macro in the end, right? to use the C ABI and say, oh, it must be exactly this bit representation as in C. But could you argue now, given this experience, that there should be a wrapper Spark in Rust to be closer to what you need?
Yes, except that there are certain cases which we haven't covered, which we didn't need for the barbecue library, but most of them we did cover. And it is similar to this morning. It is a procedure that you can follow to get the wrapper, but it's not yet the tool that generates the wrapper. So like with the railway, creating a tool that would actually do this for all the cases with automation, that would still take significant effort.
Any more questions?
So I have some probably simple question. So I guess there's some big motivation to connect Spark and Rust. There should be. So then could you slightly explain a bit of a potential reason why Spark and Rust be combined? So actually, I may probably need some more background.
Yes, so it's not only this that they are the most efficient languages. They also combine a lot of paradigms that are popular. So they're both object-oriented and therefore also imperative, and Rust is also functional. I think a big reason is that Ada has been very established in the embedded systems community for many decades, especially for software that is safety critical. So for example, one of the co-authors is from Ferrous Systems, so that's a company producing railway signaling systems. The other one, co-author, is from Ada Core, where they work on the language. Then Rust has really had quite a fast growth in usage since it was invented and released. So I think it's less than 10 years old, but there is currently an effort to write all the GNU core utils in Rust. So all the shell function, for example, ls, rm, etc., all these shell tools are currently being rewritten in Rust, including the C library functions that they rely on. So this is going to provide a very large code base of code that is guaranteed to be memory safe, which you can use. So there is really a big incentive to take advantage of this, because this code is also re-engineered to some extent to be a bit more elegant than the old implementations of the C code that go back about 50 years in some cases. So because of better software engineering practices, Rust has the potential to become a better C library in the next 5 years. So we really want to know how we can take advantage of this for building safety critical embedded systems.
It's basically then, is the Ada side, Spark side, to use Rust memory safety feature somehow?
Yes, that's in the future, I think, going to be a big direction. But also, there are certain things in Spark that are not in Rust, so that was the immediate motivation here. But I think in the long term, the opposite direction might be more important, because there's so much Rust code out there as open source code that you can reuse. And most of Ada code is proprietary and you cannot access it. So we don't really know globally what the usage patterns and data types are at scale.
Okay, thanks so much. So I said now it's a time, so.
I think you do we have more questions?
We have one, but we can clarify this offline.
Okay, or we have some discussion time also after the next talk.
Thanks for the speaker. I guess the next talk is all remote, right? So the speaker already. So okay, so all right. So can you let me know your name or sorry?
My name is Joan.
Joan. Ah, I see. So that's all right. So I guess the last talk online is a formal verification of mechanical ventilator using UPAL, presented by Joan. Right? Okay, you can go ahead.
Thank you. So yeah, I said today we're going to go through some work done by the computer science and versatile asset for the verification of a mechanical ventilator using Bhopal. My name is Joan. I'm a now graduated computer science student from the University of Delbati. And I have to issue a warning. This is a very interdisciplinary work, and I'm going to try my best to communicate some of the concepts here, but I am by no means an expert, especially regarding the physics models we're going to go through. So if I can answer a question, or if I don't go deep enough, I'll gladly pass your concerns to the more knowledgeable co-authors who are also here in the Discord ready to ask or to answer some questions. So let's dive in. So we're going to go briefly through some motivation, and that means talking about breathing and mechanical ventilation, critical systems, and formal modeling. Once you are convinced formal modeling might play a role in mechanical ventilation, and we're going to go into what a mechanical ventilator is. And that means looking at the physical plant, the general architecture, and the mathematical model that we used for a model. Then we're going to set some research objectives to sort of limit the reach of the investigation. And then we're going to talk about formal modeling, and that means explaining why did we choose what we choose, which is our formalisms and our tools. And then I'm going to actually show the model. Then we're going to talk about what we do with the model, some verification and validation results, and finally some conclusions of the future. So breathing. So it turns out that if you don't breathe, you may die. The World Health Organization recognized breathing as a vital function for survival and well-being. Actually, no breathing may cause permanent damages. So if you don't breathe for 3 minutes, for example, you might get permanent cerebral damage. And if you don't breathe for 5 minutes, you might die. And this vital function might get compromised by respiratory complications like allergies, heart problems, or that's kind of very popular diseases like COVID-19. Actually, the World Health Organization recognized pulmonary diseases and respiratory infections as the third and fourth leading causes of death globally. So when this breathing is compromised by some of these afflictions, then medical intervention is required, right? And that can be done through the usage of aids like medical ventilation. A medical ventilator is a life support tool for critical medical care, and it's a device that creates positive pressure to open the airways and expand the lungs. This is a task that healthy individuals can do by themselves, but in certain cases, patients need help with this. So we believe mechanical ventilators are critical systems, and they are life-sustaining equipment. And there are multiple reasons why we believe this. So first, there's actual human life at risk. So if one mechanical ventilator malfunctions, the health of people might be actually compromised. So as an example, if a mechanical ventilator extracts too much air from the lung, then the walls of the lung might get together, stick together, and then when the air comes back in, it might rip apart and cause internal damage that could lead to death. So that could happen like at an individual level, but at a more institutional, high level, there's dependency on medical institutions with this type of devices. You perhaps saw it during the COVID-19 pandemic when hospitals couldn't provide assistance to more patients because they didn't have enough mechanical ventilators. So if one of these goes offline, then it reduces the capacity of the medical providers. They are also very expensive, either to repair and to purchase, and they have to work in very adverse clinical environments where a lot of pathogens and diseases are around, so they have to work under very high sanitary standards. And they're also technically complex inside and outside in terms of the concepts the medical professionals use. So to behave exactly the way the medical professional wants to, it And lastly, it is also used as a real-time monitor, so the sensors read some valuable information from the patient. So a medical expert might look into the data that the medical ventilator is reading and then take decisions upon it, decisions that might have a big impact on the patient's health. So for all these reasons, we believe medical ventilation fits in the category of critical systems. And critical systems have this characteristic of being dependent normally or usually on real-time requirements. This has been actually been detected with mechanical ventilators where time desynchronizations and wrong configurations have been linked to possible worse health outcomes. And as said, some of the requirements of these devices are real-time requirements of these critical systems that go in the shape of the ventilator will not inject air to the patient for more than 5 seconds, right? And these type of properties are in charge of the controller, which is an embedded system that must be programmed. Then to develop this type of software, it goes through the usual phases of software development, and we believe that in the software requirement phase, formal modeling could be applied. So before the actual code is implemented, we need to propose a model that we know for sure that actually fulfills the real-time requirements. And for this, different tools can be used like Upal, Scale, or perhaps MATLAB. So hopefully I convince you that a mechanical ventilator is a critical system and that formal modeling can be applied here. So now we're going to go into what a mechanical ventilator is, or at least the one we use for this work. So right here you can see photos of it. This is an actual mechanical ventilator that the mechanical engineering faculty uses as a part of the VentiNet research project. It's actually being used to train medical students to operate these devices. Usually the mechanical ventilators have 2 modes, assisted and spontaneous. And when it is set to assisted, then there are 2 ways or 2 modes of control, either controlled by pressure or controlled by volume. And the general architecture looks like this. So there are usually 2 sources, one of pure oxygen or very pure oxygen, which is usually a pipe, and then a source of air, which could be a compressor, and they both go through a set of sensors and then a set of valves that regulate the mixing that is being done in this mixing tank, which is depicted here as a square with white to green gradient. So these valves try to mix to form enriched air in the exact rate of oxygen, pure oxygen, and air. And once that is reached, then the mix has to be delivered to the patient, and that is done through the inspiration lane. So that also has a set of valves and sensors, and if the expiration line is off, then the inspiration line could open, and the difference of pressure between the patient's lung and the mixing tank creates an inward flow, right? And once the inspiration phase is over, then the inspiration line shuts off, the expiration line opens up, and then difference of pressure between the patient's lung and the exterior creates an outward flow. And that's basically it. There's 4 sensors that are used to be for internal control, but they're also shown or visualized by the medical expert. And there's a filter here that basically retains pathogens and molecules that cannot be just lured into the exterior. And yeah, that's it. So for this work, we decided to model this device as a set of relationships between, let's call it a source right here, and an accumulator. The source might be one of the oxygen or air sources, and then the accumulator would be the mixing tank, or this source would be the mixing tank, and then the accumulator would be the patient's And this source and accumulator is connected by a pipe, where if we suppose laminar flow, then the flow is characterized by the Reynolds number, which you can see on the left, which depends on the viscosity U, the diameter D, and the length L of the pipe, of the channel. And this Reynolds number is the factor that relates pressure to flow of the fluid. Then in general, we could say that the flow between the source and the accumulator depends on the difference of pressure of the source and the accumulator. And then in terms of measures, the pressure delta, that difference of pressure depends on delta T, which is the delay of sampling. And this will be a case for study later. So let's limit our research and establish some objectives. So we plan to propose a formal model of mechanical ventilator architecture we just saw, then verify some properties over such model, and lastly, do some validation regarding simulated results compared to experiment conditions of the physical plant. So to model, we chose the time automata formalism, more specifically time automata with inputs and outputs, which is just a time automata where the actions are split in two sets, one of inputs and one of outputs, and these actions are can be listened to, can be listened by other automata and then synchronized through them, making like a network of time automata, right? So as an example, you guys can see here a time automata with inputs and outputs that has one transition that has an output A, and that could mean that another time automata is waiting for that action, or it has an input A, and it's trying to, or expecting, or waiting for this automata to synchronize, and then this lower transition has the input B and is expecting other time automata to do B question mark, or the output action B to synchronize with. And this network of time automata, or time automata with inputs and outputs, is the basis of the modeling tool UPAL, which is a tool for modeling, validation, and verification of real-time systems. And it is actually like a tool set, and one of the tools that comes included is the UPAL statistical model checking SNC that replaces non-determinism with probabilistic choices, and that can be used to do some verification, some property verification that can be expressed, or with properties that can be expressed with a simplified version of TCTL. So for example, a symbolic property would be something like that, that says that there exists a path where x greater than 1 eventually holds, or a probabilistic property that says that or asks what is the probability of x be greater than 1 eventually holding within the first 10 time steps. And to the left, to the right, sorry, you might see the UPAL UI and a very simple model of a coffee machine. Right? So this is the tool we used, and now we're going to go through what the model actually is. So we have 4 models, 4 time automata with inputs and outputs that form a single network of time automata. The first one is the setup, which is responsible for setting the initial parameters of the ventilator, including flow rate, duty cycle, and FiO2, which is the fraction of inspired oxygen. And then it's like the main automata, or the main template, which is the control one that oversees the configuration, mixing, inspiration, expiration, and pulse phases of the ventilation process. Roughly, you can see here 2 loops, the left one being in charge of expiration, and the right one being in charge of the inspiration phases. And lastly, the injector, which is this little motor up here, which is a supply line that delivers either oxygen or air to the mixing chamber, until the desired fraction of inspired oxygen is reached. And then down below, the So this is the model we propose, and we managed to get some verification results. We proposed 40 models in the article, 40 properties, sorry, in the article, and the last 4 used SMC, or statistical model checking. We verified both symbolic and stochastic properties using the same model, and we reached the conclusion that the model adheres to the specification given by the properties of safety and liveness. So I'm not going to go through all the properties. As an example, here is property 5 that states that it's symbolic and states that it is possible to reach states where the injectors are on. So basically the mixing gets eventually done. Or property 10 that makes use of SMC that basically tells the probability of reaching the inspiration state to early over 500 runs. Right? So in the paper, the results are consolidated in tables 2, 3, and 4. The symbolic properties 1 to 9 were satisfied under different inputs and configurations, and then the properties 10 to 14, which are that make use of SMC, were also satisfied. As an example, property 10, which is a liveness property, says something bad should never happen, has a very low probability of actually happening. And on top of that, we use the model to do a comparison with the physical plan that actually is in the mechanical engineering faculty of the University of Del Valle. We chose to compare the flow rate values of a single whole cycle. So that would mean how much fluid goes in and out of a patient. And that can be computed in the model with this SMC query and by the sensor readings of the physical plant. And we run both using different delay times delta t. And the results, at least visually, are good. You see on the left the results of our PAL model, and on the right the experimental readings of the physical plant. And I guess you can see resemblance, right? And if you look at the relative error respective to the desired volume B, which is defined here, you might see first in the model that reducing delta t has a big impact on that relative error, right? And if you try to do the same over the actual physical plan, you get a considerable impact too. You reduce the relative error of the respective of the desired volume down from 5% to 3%. And that will translate to a difference of around 10 milliliters of oxygen-enriched air delivered to the patient by simply taking samples a bit earlier. So in critical situations or with specific patient conditions, even such small changes in exhalation can have a relevant implication for patient care. So as a conclusion, we believe that the primary contribution of this work is the development and analysis of a formal model of mechanical ventilator, which we believe has not been done before in PAL. We verified some safety and liveness relevant properties over that model, and we also provided valuable insights into the selection of an optimal delay time, delta t, supported by our model. We believe that this approach could set the stage for future modeling and verification of such devices without compromising necessarily expressiveness. And as a future work, we could consider refining the model to include other characteristics or other environmental influences, basically make it a bit more complex and let's call it realistic. Or perhaps use real-world data and test cases, perhaps have some medical experts play around with it, or consider other formalisms and tools like scale. I think we actually did think it around with at the beginning of the work, or perhaps using real-time mod. We're looking actually into some recent findings of the relationship between time automata and rewriting logic to see where rewriting logic might play a role in
Thank you very much. Do we have any questions?
So, thank you so much. It's a very nice talk from the other side of the world. So I have a few questions. So my name is Peter Oveski. So first of all, this sounds like, I mean, that's also why we're very happy that this paper is accepted here, because it sounds like a very good, in general case study, right, for, real-time tools like, real-time mod and so on. So my first question is there enough details? There's enough details about the modeling paper that this can become somehow canonical case study, right, so that we can actually model the system, right, or some pointers and so on, right? So that's my first question.
Yes, actually, the models are available online, and we're doing some other work related to the simulation algorithms and detecting mutants, permutation testing, and we actually try to use this mechanical ventilation model. I mean, it's up to the community to see whether this becomes sort of like a benchmark, like other available.
Well, it sounds like a good one. So yeah. Okay, so my second question is, so I mean, is this some kind of design you came up with, or is it taken from some kind of industrial design of a mechanical ventilator, or is it just more like toy sort of example that you came up? This is how it should look, or so? Is this a realistic model of a ventilator?
It is I mean, perhaps, Professor. Well, I'll try to answer. So this is a realistic model of a very bare bones mechanical ventilator. So it might play the role, and it might not be the best mechanical ventilator because there are some other components that might, for example, ease the transition between not being held by mechanical ventilation and then having the assistance, or there might be some small details. And there's also the observation that we just model the assisted mode under volume control, right? So there are some other modes of operations that are not included in the model.
Okay. So sorry, can I have one more question? Or but in general, right? So when you verify the systems, typically you have to verify the system together with its environment. But you have not done you don't have a model of the sort of human bad lungs or something like that, right? So human ventilation system to verify that your system is actually correct, right?
Yeah, that's the correct observation. Actually, the lungs of the patients are not like a fixed tank, but I have a very, very complicated behavior. It's actually not like a single container, but lungs actually have like very little small containers that contain the bigger lung. So we try to go into a bit more detail, and that's what we meant on refining the model.
Yeah, so future work, yeah.
Yeah, with some other characteristics. You're correct, yes.
Okay, well, thank you so much. So sorry, I'll give it to somebody else. Okay, so Mario is the question. Thank you.
Yeah, thanks for a really insightful case study. My question is regarding the statistical model checking. Can you maybe say a little bit about which parameters are at hand in UPAL to increase the confidence in the verification results?
Oh, I'm not sure about that one. David, could you?
Yeah, I think that. So hi, I'm another co-author of the paper. What with parameters? What do you mean exactly? Sorry.
So my question is based on the on my assumption that statistical model checking cannot provide a guarantee in a sense of probabilistic model checking, but of course a good approximation of it, of course. So I was wondering whether there's some adjustments, but UPAL offers adjustments where the confidence level in the approximation can be I don't know, adjusted. I've not used UPAL, but I'm just wondering whether you came across such adjustments.
Yeah, we can definitely set a confidence interval and also many other stuff, as you mentioned, like the state representation used, the distribution as well. So yeah, we can set those kind of parameters like confidence intervals, the distribution, etc. We didn't have to exactly delve into those kind of parameters because we believe the defaults are already reasonable. For example, confidence intervals are only 5%. The, the distributions used are normal distributions, which were, let's say, aligned to our study. So yes, people, those offer you those kind of adjustments, but we didn't came across needing to change the defaults.
Oh, great. Thank you very much. So my question has the background that in certification practice, people seem to raise these questions every now and then. So it's not a problematic question. It's just a question that one might ask, perhaps. Yeah. Okay. Thank you.
Segregation. Thank you.
Thank you. Any more questions? We have more questions.
There's a quick question. It seems that probably is based on mechanical modeling. So I guess probably the physical model was initially given by some differential equation, and then but you changed to some discrete system by time difference, right? So is there some original differential equation model? That's a question. For physical part.
Yes, there is one. I do not recall exactly what, but this is actually, yes, a very watered down model of a set of differential equations that are actually part of another related paper done by the mechanical engineering faculty. But I cannot provide you the details. Yeah, there is one. Yeah.
Probably can find it from paper, right? So the reference from paper.
Yes, there's one by, I believe Professor Jose Garcia, and I think Andres Valencia is an author there too, and they both talk about the Ventinet project and how the
Ventinet project.
Right there, they have the reference to the models.
Okay, great, thank you.
So you're currently using time automata where time obviously moves only one direction. What if you were to include other physical properties like airflow or air pressure, which is not always going one direction, it can go up and down? Could you still use a tool like UPAL for a richer model, or would you have to use a different modeling formalism?
Sorry, wait. Anyways, so I'm not sure. There's a supposition of laminar flow, which is a big supposition, a big assumption, and I'm not sure what the limits of time automata are actually for this. I don't know. Perhaps Professor Hames could help me with this. No.
Okay. Well, it's also not my domain, but thanks. And just a remark also, I saw you have a GitHub repository. Please add a license. We've had this several times. If others, if you want to give permission to others to use your code, you need to add a license. Then it's legally safe for others to use it. Thanks.
Okay, so thanks so much. Oh, Peter, one more question.
So maybe not so directed to you, but you use UPAL SMC. So what kind of distributions, probability distributions, are supported, or is it user diff? So what can you? You mentioned normal distributions, I guess uniform. So what do you know about? Maybe it's not a real question for you, but I mean, since you gave a talk.
Yeah, I'm actually just looking at them right now. There's normal. I think there is. Sorry, I'm just looking at the UI. Yeah, there is normal. There is lambda distribution as well. There's there's a bunch of them. There's a lot of parameters that you can set. The propagation order, the search priority, some strategy, extrapolation, also learning filters, learning methods. we can have a lower probabilistic deviation, which is minus delta, on upper, false positives, false negatives as well. The ratio of the lower bounds, the uncertainty as well, which is 5%. Also some errors and discretization steps when you're dealing with hybrid systems. So yeah, there's a lot of things you can set.
Great. Well, okay. Thank you so much. Thank you.
Okay, I think that is a normal question. So thanks so much for your talk. So and then I guess that the last part is the some discussion session by the chairs. So.
Yes, so welcome all of you to join the workshop. Without your participation, we wouldn't have the workshop. Of course, also thanks to all the speakers. Now, there were maybe one or two questions that came up in the meantime or which you didn't have time to ask, so we can start with that. Is there anything you would like to ask about one of the presentations that you couldn't ask earlier? Like Mario, you had a question that you couldn't ask, and I don't maybe you remember.
It's not a Nobel Prize question, but yeah. It was a really nice insight into language bindings or bindings between languages. The example you showed suggests to me that there's a lot of synchronization primitives implemented in the grant read and write grants, right? How do you? I was just wondering, because I don't know either of these languages in detail, on which atomic primitives do they, so how is the test and set implemented, and whether this has some impact on your proof obligations that might eventually come out of the effort that you're attempting. Does the question make sense?
Yes, I don't know in detail, so I'm not 100% sure if I am giving the right answer, but I assume that this is implemented with specific hardware support for incrementing a counter or checking it atomically. So probably it uses the same underlying implementation on both sides. You
so
just have to make sure it uses the right one.
Do you think they are using C or directly or even below the operating system stuff directly? Or some C library which
well, at least it is accessed through a C library, okay. But I'd have to ask the student, who is unfortunately not here today. So
no worries, but anyway, thank you. That was already
Any more questions?
Okay, thanks. Then we have closed the technical questions, but now there is maybe a more general discussion for the next up to, say, 20 minutes. How do we continue? Is the application of formal methods in general something that can warrant its own community and workshop? The workshop that we've had for the 8th time. Is the workshop in the right new home here? Because after COVID, because of scheduling reasons mostly, we decided to try to collocate with a different event. We used to be with ICFEM, which is quite a similar target audience like this one. Now we are with SPLASH and OOPSLA, where there is some overlap. For example, we have SAS, which is about code analysis, but the overlap is sometimes also at the same time. And the main conference maybe doesn't provide as much of a synergy as we were hoping, and so we didn't get a lot of papers. Maybe we didn't get so many papers because there are other events like ATWA and I think PLDC and ESOLA. So the timing was quite unfortunate this year. So we wonder a bit if, from your impression, do you think there is a potential to grow this event again in the future? Is there maybe another conference that you would really like to attend where it would be easier to collocate this with? What are your opinions? It's the second time with Splash. Okay. Yeah, so we had it last year in New Zealand, and we got about twice as many papers and at least about double the crowd, a bit more for the morning keynote, and then a bit less for the presentations. So it was also in early December, I think, last year. So it was quite a different time of the year when there are no other conferences that are important, so that helped probably. And the location was actually quite remote for almost anyone, and that didn't deter people from submitting papers. And we thought that this year in Europe it's a little easier. I mean, Portugal is quite remote within Europe, but at least it's still a short-haul flight for most. So we thought there would be more people than in New Zealand.
I have maybe another best guess that could also be a cause for fewer submissions. The IFM and CEFM were roughly at a similar time regarding the submissions.
Yeah, the deadline is important.
The deadlines are important, and also even these two conferences, they overlap quite strongly. So even they had problems with soliciting a number of papers from the grapevine. I heard that they also had comparatively few submissions.
How many did SCFM have?
No, IFM and SEFM. Yeah, I don't remember it by heart, but I can have a look. But also the other more meta comment that I wanted to give is there is a range of venues that overlap topic-wise, and if they all take place regarding the submission deadline within a few weeks, I think it has become harder. Yeah.
Yeah, actually, also ICFEM had a very disappointing turnout in the submissions this year, if I remember correctly. Something like 45 papers.
And the last comment, maybe adding to that, is my also impression that currently the trend in AI and ML draws in quite a few formal method submissions. So it could kind of combine a little to the detriment of the traditional venues. That would be my hypothesis.
I'll also give my 2 cents here. Maybe what you were suggesting, having a conference which is more either towards formal techniques, formal methods, or safety critical systems could help keeping people in the loop, and they are maybe already kind of thinking about going there. I don't know, DSN, IFM, SEFM, we've named a few here. Maybe the stronger link, or SafeComp even, can help with the submissions.
Yeah, so one candidate we had in mind just tentatively is ATWA next year. ATWA next year would take place in Kyoto. I don't know when. When I asked the organizer, he didn't even know yet when exactly. But it would be a very attractive location. And one danger is also that we don't want to have the exact same scope as the main conference, because otherwise it's just a collection of rejected papers that you get. So ATWA has a closer fit, but is not exactly the same, so that could be nice. We want probably something like that. We were hoping the same from Splash and Uppsala, but it's maybe a little bit too much in the direction of analyzing or working with software, not necessarily analyzing software, but it's less at the systems level, so that the joint part of the audience is maybe a bit too small.
There is Embedded Systems Week and CPS Week as well. So I wonder whether you have considered these week events.
Aren't they usually in the US?
Embedded Systems Week, I thought it was in Europe. CPS Week is normally in the US, yeah. That's true.
We don't want to go there.
Well, I personally haven't attended these events before, but it could be an option if it's not too often in the US, if it's like every...
Oh, CPS Week was in Portugal, actually, last time it was 2017, I think it was in Portugal. Oh, 18, yeah.
No, but it's, we had a paper themselves, right, so a few years ago. So yeah, we...
So I guess Peter's and my personal preference are also countries where it's not too onerous to travel to in terms of all the security theater and like ESTA and all this that you have to get. It's just like extra work and maybe places that are nice to visit, which is the case here. We have not enough time this time to really enjoy the venue. That would also be the case in Kyoto, obviously. There's so much to see there that it's a great destination for anyone, so this could increase the audience also.
There's another multi-conference, not every year, FLOC, which is usually, as far as I know, in Europe. And FLOC, and I wonder, because I don't know how much, how safety... It's only every 4 years. Yeah, oh, okay.
Last year it was in Israel, in 2022.
Right. Okay.
So probably it's already written somewhere in the web, whereas in 4 years to come. I don't even know. Right.
Okay, that's not practical. Okay, thanks.
Okay, but in any case, we would be looking into late 2024 or early 2025. I mean, because there are so many events in fall, it might actually be good to have something in spring, but then we'll have to see if the deadlines are suitable for us, and not only to submit, but also to review. One advantage was that in the past, the deadlines tended to work well with other conferences, that we were able to kind of snatch papers during a window when there was nothing available otherwise, but this time we had the opposite, that we were competing with other deadlines.
So I had a question more about like the general topic of the conference. So like when you say the formal method for safety critical system, like anything that I think of in formal method can be applied to safety critical systems. So
point, right? That's in general.
So like, because I wanted to submit a paper to this initially, but then I was not sure if it's a fit, like if it's, if it even makes sense to submit here. I submitted to PPDP and it was rejected, but it's a different thing. So I think there is some option there to make it more elaborate, like what topic you are seeking, and so it's clear to the authors that, okay, this is a venue where a paper would be a good fit for.
Yes, it's not so easy to change the title without changing the acronym, but maybe we just want to make clear that security is also quite welcome, I think. We didn't have anything about security this time. We had one paper that was not quite polished and not so clearly focused, which was about security, which we didn't accept among the submissions. But we actually also welcome formal methods about security. Now, FDS SCS is a bit too long and clumsy, so we might have to just make this clear in some way without changing the name. Maybe formal methods for safety criticality and security. It could be a way to rename it. But yeah, we'll continue to discuss this offline during the coffee break and after. So we still have to wait 10 minutes or so probably before we can get coffee, but we'll see. So it will soon be ready. And then I'd like to thank you all for staying until the end. And
thank you, everybody. So
then let's enjoy the coffee. And thanks to the organizers too. dinner at 5 at one of the cafes at the beach would be nice, because between 5 and, so after 5 you have to wait until 7, and then it's quite late. There's nothing between, after 5 the cafes close, and then the restaurants don't open until 7, so you can...
so funny, so even before 5
I see what you mean. I think this setting is not good.
I was comparing to room number 2, and they had also a remote speaker.
Yes, and that was fine.
It was erect.
Yes.
It was a great volume, great sound. And on this one, it was very far away. You could listen to it. You could understand